I believe so. Good.
Oh, there's I had no idea what you were eating.
Yeah, I wasn't sure either. What? Excited to have the opportunity. So I'm excited to have the opportunity to present. It'll be good fun.
Max, why are you picking on chairs? What's up? Why are you picking on chairs? Because I brought them here on the previous session. Oh, you take them back? Yes. Oh, I take them back.
Pretty soon.
Yeah.
It's working. We're streaming. Yeah. How exciting. So.
This is a new experiment?
The slides I'll be following along if I can, or we can point it at the screen. If y'all want to stand in this area, I think the camera and microphone should pick you up. If you don't, it's just for the stream. Like there's the extra viewers if you like. Yeah, many things like presenting here. So it's another minute or.
Do you have this?
Yes.
Still missing characters.
Yes. So she's got time.
Oh, so she's got.
Yeah, she can roll up. I think it's like 2 hours from now, right?
Okay, so you don't know that she's not a quantum psychiatrist.
Yeah, I don't know. I haven't heard. Thank you very much.
It's been doing the rounds. Yes. I wasn't taking a sense.
Oh,
Started.
no. Anything good in it? Maybe Dr. Hoolan's. This is his laptop. So, could be him. Well, I guess if other people trickle in, that'll be fine. But I guess we'll go ahead and get started. So, welcome and Bill Coleman and all that good stuff to Haptics in Education, the workshop today on Haptics in Education. So, today we're going to hopefully explore the role of haptics in learning as the title of the workshop would suggest. And I think it's a really exciting time. There's a lot of different groups all over the world working on broadly haptics in education. So bringing a lot of different perspectives, a lot of different subject materials, a lot of different topics. I think it's really great. So I'd like to thank my co-organizers who are mostly here, and I think Faustina's watching online. So thanks everybody for all your help. I'm really excited about it. So I kind of have two goals, I think, for the workshop would be to update the community with the latest and greatest of what our speakers are going to present, and then hopefully tease out and nail down some principles or best practices or some guidelines for why we should use haptics and how we should use haptics in teaching and pedagogy in general. So a little brief background about me is that my main teaching experience has been in Dr. O'Malley's junior level system dynamics course. And so that isn't a whole lot of formal training, but it's mostly a see one, do one, teach one kind of thing. So we get to do it for 3 years. So the first year you're kind of just watching the older TAs or lab proctors handle the labs, and the next one you're doing them, and the third time you're trying to teach the next group how to proctor the lab. So it's really good at developing like legacy, like things you should do and how to fix broken hardware, but it's not much in the way of like formal, like how you should teach. And so I was thinking, as I'm looking until hopefully into the near future, I'll be like making my own course and hopefully complementing it with haptics. Like, boy, I wish I had a group of experts so I could get into one room to tell me like why I should use haptics, how I should use haptics in education. You know, what are the curricular, guidelines I should use? How should I design the hardware? How should I design the curriculum to fit the hardware? Which order should that go in? And then like the further along I got on this list, it kind of seemed like I should just have a workshop where I could get that all in one place. So we started planning it. Then we started talking to Will and his group, and they had a similar idea with looking at how haptics can be used in a broad education. That would be a great workshop to have. So kind of I guess for more background about what I've seen and what I'm used to is the haptics that Rice has for this junior level course. So it's a system dynamics course where the kind of the main focus is for mechanical engineers to get their hands-on experience with modeling and interacting and tuning with second order systems. So a lot of SysID and second order like step responses. So the first time the haptic paddles were adopted and adapted for use was to try and generate a unified lab curriculum for this course. So instead of a bunch of separate isolated experiments, trying to create one cohesive story. And so NSF funded this experiment to compare students who received the separate curriculum with students who got this kind of nice haptic paddle story where each lab built on the other. And so found that there were significant differences in student learning, so students learned more when they had the cohesive haptic paddle labs. So this was a similar implementation to some of the first haptic paddles with the capstan, cable transmission, and some hardware, some implementation hardware provided by National Instruments. So the second kind of iteration of the haptic paddles at Rice, we're trying to get the the labs to be more in the hands of the students. So as opposed to kind of watching the TA or the lab proctor, set up the hardware and run the experiment, we wanted the students to be doing it themselves to try and increase the uptime and like the interaction, like the exploratory nature of the labs. So the paddle was redesigned to lower the perceived and real costs of breaking the paddle with an unstable configuration, so moving away from the capstan cable transmission towards the friction drive, which a lot of groups have implemented, and then trying to move away from the PXI chassis, which is a little more black boxy for the undergrads, more moving towards the MyRio and the MyDAP architecture, which is really friendly with the graphical interface of LabVIEW. So students were used to that from previous classes, so trying to keep that kind of connection between the different courses, hopefully improve their amount of interactions. So the third thing we looked at was trying to expand the curriculum. So the first step was trying to improve the haptic performance of the Haptic Paddle with some minor tweaks to the design, which, shameless plug time, there's a demo. You can come see this new thing, and you can see the undergrad who led this design work, Nathan Bucky. He did a lot of great stuff, so shameless plug over. But we improved the haptic performance of the Haptic Paddle, and we were able to add some modules like other groups, and we'll hopefully hear about a couple of them today, about modules you can add with Haptic Paddles. We added a dynamic plan, a ball and beam, which is like a classic model for mechanical engineers, and looking at trying to use that to have a dynamic teleoperation, so instead of two identical paddles following each other, which maybe isn't as cool as something that's dynamic, and you kind of get the benefit of unilateral and bilateral teleoperation for the students, a little more obvious. And moving towards some advanced topics later on in the curriculum, so some linear control theory, which is kind of at the very end of this course we kind of tease, but trying to give students another chance to really look at that, as well as enable like advanced topics in mechatronics and haptics, looking at using this ball and beam for like visual motor experiments. And yeah, come on in. And studying the effects of haptic guidance or air augmentation on visual motor tasks. So we thought we've done all this great design work, and we built like 3 different versions of the paddles. These are amazing paddles, the best paddles ever. But still, we're kind of like student interest. It's really great. Like the last lab where we have teleoperation, virtual environments, students are really jazzed about it, really excited. But there wasn't a lot of connection between the previous lab. Students were like, it was great seeing the paddles, but like, why do we have to do all the SysID leading up to that? Like, why can't we just have the cool stuff once and never come to lab again? So we thought, okay, so there's something we're missing. And the Rice Center for Teaching Excellence has been around for about a decade, but they started in right when I was doing this, like fall 2012 through 2015, they had a lot of workshops on some like active learning in STEM, some like flipped classrooms in STEM. It really started kind of getting me thinking like maybe there's more than just designing a really nice paddle. Maybe there's more to this. And so there was a conference called Teaching at the University Tomorrow, which really kind of, told me there's more than the see one, do one, teach one way of learning how to teach. So we kind of pulled a few papers and a few discussions from that kind of conference, and we particularly started looking at Kolb's experiential learning cycle, which is like probably a really simple, basic one, but nonetheless I thought was really, I guess to me, it was really eye-opening, because it's like, I think we had really nailed down like an active experimentation and like a concrete experience. Like, yeah, students did a real experiment in the lab, and they were kind of hoping that like, yeah, they'll write a lab report and then they'll have conceptualized all the abstract stuff we're trying to get them to learn. Like, why doesn't that work? And so kind of looking at this model, we were like, oh, maybe they didn't reflect. And reflection is like the big buzzword now, so we're like, okay, let's really start looking into this more. So we did a 2-year study comparing students receiving our typical, curriculum with the curriculum that was designed to have some like reflective interventions, some points where we force the students to stop and think about like why we were doing the labs, why we designed experiments a certain way, trying to get the students to design the experiments before coming to the lab, so try and turn the lab, instead of this really well-oiled task, checklist that you have to, make this measurement and then you can leave, more of like a, self-motivated, like, I need to figure out why the paddle does this, or I need to figure out this parameter to try and improve it. And so we found that there was, across 3 GPA quartiles, there was significant or near significant difference to students receiving this reflective curriculum. So it was encouraging results. And these were pretty modest changes, so we thought that's pretty interesting. So enough of that. I'll want to get straight to the speakers. So I guess a kind of brief introduction of all the speakers today. We've got 6 speakers who are going to give us a bunch of different perspectives. We're going to start with Roger and Olivier talking about their hands-on approach to education and physical human-robot interaction. Trevor Smith from SLU is going to be talking about the Haptic Paddle is a teaching tool in system dynamics, so probably similar to the stuff I just bored you with. Volkan's got hands-on SCA that I'm really excited to see. It's kind of the same modular approach. Karen, who'll be here shortly, is bringing her take on the design space of teaching with haptics. And then Melissa has got the new Hapkit, and I'm sure a lot of other great things. I'm looking forward to it. I'm really excited. And then Megan's going to be kind of closing us out with a pedagogy kind of expertise, and so it's going to be great. And then Ed is going to be our raconteur, trying to tease out these principles and why haptics. So enough of that. Oh, almost got you. So broad questions. So yeah, almost in. So one thing we've encouraged the speakers, and I would love to encourage the question in the audience to kind of, we're trying to answer some of these broad questions about why we should use haptics. So these are on the website. We had some revisions on them, so if you looked at it a while ago, they have changed a little bit. But kind of the questions that I'm looking to get answered for my own benefit would be what do you think is necessary to go beyond novelty? So students, of course, it's fun to play with it, but we need to do more than that. And then what is more motivating, you building the device or using one to get a feel from a concept? So is it only beneficial for mechanical or mechatronic engineers to build the device and say, yes, I made a working device, or is there some other magic we can work? Moving these to very large scale, so I think that's something that some of us have looked at, some MOOCs and that sort of, democratizing haptics. I think that would be a great perspective. Should we augment haptics with low-cost, virtual or augmented reality? Do these supplant or usurp? How do they interact? I think it's something that I know nothing about. I'm looking forward to learning. And then, what key characteristics of subject material are required for educational content to be hapticized? Is there something that, can anything be hapticized? I don't know. I hope you'll tell me. And then, where are the big or easy wins in the future? What sort of training and tools that content creators need? Is there some sort of formal thing that people should, sort of a primer on haptics in education? And then fostering and assessing active reflective learning is kind of something I'd like to learn more about. So with that, I will pass it off.
All right, thank you, Chad, for the introduction and also for the invitation to speak at this workshop. It's a great pleasure to be here and have the chance to give you a little bit of our views on how to use haptics for education, in particular in physical-human-robot interaction. So, I get this thing to work? Yeah. All right, so physical-human-robot interaction is a relatively growing field, and it covers a wide range of applications, from normal robotics to, for example, robotics for assistive technology or rehabilitation robotics, which is the primary focus of our lab. And in these different topics, haptics plays as a fundamental component. You need to understand the requirements from the human. You need to play with perception and action. There's of course a high part on interaction control, and also you need to be able to evaluate the performance and the safety of your devices. But this is physical-human-robot interaction is a very practical field. It's interdisciplinary. It covers a lot of different fields, and it makes it a challenge for placing it into education. Also because it's practical and you kind of need hardware in order to really have a feeling for these concepts. So if we now look a little bit about studying in Switzerland, this is really specific to the Swiss system, but I guess it can also be transferred to other countries. So you typically have mandatory education until the age of about 15
Concepts.
and then students can choose between.
So if we now look a little bit about them, but I guess we can also be transferred to
other countries. So you typically have mandatory education until the age of about 15
concepts.
and then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you typically have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you typically have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you typically have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts.
And then students can.
So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts. So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts. So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts. So if we now look a little bit about them, but I guess we can also be transferred to other countries. So you have mandatory education until the age of about 15 concepts. So if we now look a little bit about them, but I guess we can also be transferred to other countries.
We want them to manipulate conventional mechatronics components and also build their own haptic device from the beginning till the end. And maybe a more general idea, we also want them to familiarize with the research environment, working in a team, which is something these students pretty much never done before, and try to think about the problem, not just give them something that they have to implement, but really a problem that they have to think by themselves. So what we come up with was the development of a haptic simulator for spinal anesthesia. So spinal anesthesia is a rather simple procedure which consists in inserting a needle in the back of a person. So you go through the different layers all the way to the spinal canal where you then inject some drug for anesthesia. So why did we choose such a task? Well, there's a clinical motivation they can relate to this type of intervention. As I said, it's a rather simple task. You can simplify it to single degrees of freedom needle insertion. There's available literature where you can find relevant information about properties of the layers and inserting needle through soft tissues and so on. And you also have the ability to compare your measurement with a real device, not a real subject, but a real phantom to plastic rubber phantom to have comparative measurements. So this is what we asked them to do. So develop the whole haptic device, including the design and the control aspect. So what they had to do in different subgroups, had to look into doing measurements on a rubber phantom, get some data from literature, so they have access to laptops and internet, so that they can go check some papers on these procedures, all the way to build a model of different layers that should feel as realistic as possible. Then they have to design prototypes, so for this purpose we give them some kind of Lego-based boxes where they have all kinds of gears and components, but they also have mechatronic components, maximum motor, data acquisition cards, and potentiometer, and amplifier. And of course, they have to then implement the right transmission ratio in order to get the forces they want at the end, given this hardware. Then they also have to implement the control. So we typically give them an introduction to LabVIEW, and they have to implement haptic feedback by controlling the motor, but also visual and auditory feedback. This is just an example of having, for example, a spinal cord with different tissues that they have to penetrate with the needle. So in terms of costs, the whole things cost about $1,000 for one group, and we provide them 2 laptops, computer per group for the whole week. But the schedule looks a little bit like this. So we give them on the first day, so it's a whole week. We give them on the first day some introduction and lecture about studying at ETH, what it means, what it is, and then some lecture about control, and the mechanical designs, and literature search and modeling. Then they have different phases where they can work as a group. There are 2 assistants from the 2 PhD students that are assisting them during the whole week, and they also their math and physics teacher that stay with them. And in between, they have daily meetings so that we can check the progress and also refocus them a little bit. And they also have deliverables after pretty much each day, where they have first previous planning, then there's a report at the end with a 3-4 pages report. Yeah. And then the last day, they have some presentation, and everybody gets to try the different prototypes during live demos. Just a quick view on different challenges. So, of course, with respect to the measurements, they have to face the challenges of seeing what kind of data is enough. Like, how do when I make measurements, is it sufficient to take just one measure? Do I have to take more than one? What happens when the literature values are not the same as the value I measure? How do I deal with that? What can I find as an acceptable compromise? In terms of mechanical designs, which sensor to use, how do I place it? What kind of transmission? How do I minimize the friction? Of course, they are using some rather simple components, so this will be issues they have to face. How to manage with these limitations, and how to make the prototype more original. In terms of the control, we asked them to implement some stiffness and damping. How can we do that? Those students don't know how to do derivatives, so they have to also learn these aspects, learn the effect of sampling control, sampling frequency, making a control loop, and of course they have to figure out what is good enough, when is my system good enough. So just a quick word on results. So we did this 8 times already between 2010 and 2016. So we touched about 250 students from 3 different colleges. And what was very nice to see is that every time at the end, all groups had a working prototype that they could test during their demo sessions. And there was a very wide range of solutions. You can see here a few pictures of how these final prototypes may look like. Some are compact, some are less compact, some use chain transmission, some use gear transmission. I mean, there are really a wide variety of solutions. They are really free to do it the way they want. Same thing for the visual feedback. Some is rather simple with just a few layers, some have different angles, and texture and so on, or you can customize to the different features of the patient. In general, there's a quite high satisfaction from students and the accompanying teacher. So we, at the end, give them some questionnaire. I won't go too much into detail for the sake of the time, but usually they find the task interesting. So the statistics of 4 years. What is sometimes a little bit more difficult is for them to understand the question. They are not used to having an open problem that they have to face by themselves. They prefer to have just simple question that they can, where the answer is easy to find. So this is a bit challenging for them. Same thing with time management, sometimes a little bit tricky. But in terms of infrastructure and support, it's always very positively graded, and also as surprise to us, they like to work as a team. It always worked out pretty well. And maybe a final kind of statistics. So we looked into who then decides to go and study at ETH, and we consistently have about 20 to 40% of students that continue that decide to afterwards go and do their study at ETH. A good portion of them going into mechanical engineering. And with this, I give the word to Roger, who will now talk about our PHRI course.
Thank you, Olivier. Thanks also for the invitation. So what you've seen up to now, Olivier has been really strongly involved in, and he's also been very strongly involved in this part here. So after we started the lab end of 2008 at ETH, we wanted to have a course where we can really get in touch with students that are interested in the field in which we work. And for that we took something over that's has been used a lot with a lot of success, especially in the US, and that's related to this open hardware around the Haptic Paddle. And we didn't change it a lot. We changed it to the metric system, obviously. We also decided to go for LabVIEW, and there's actually a USB data acquisition card in the back that we used. And we made our own, designed our own power amplifier, so that the students are really controlling the torque on the motor directly. And they get this, they get the thing set up, but they have to cable everything, and we then walk them basically through all the components that we think are important. So the course starts with a look at human factors and safety. This is something they haven't touched, especially the mechanical engineers. They tend to, they tend to only look at the engineering part that they have to work on. Then we look at sensing. So they hook up the sensors. They learn how to read them out, how to process the signals. We look at actuation and kinematics and transmissions. We go over to data acquisition. How does it change when I go from offline processing to online processing? And then we look at things such as modeling and simulation, and then we switch over to interaction control and also characterization. And that, again, we do from both the engineering perspective and the human perspective. And so as Olivier mentioned, we have 13 setups, 14 actually one for us, and so we have been limiting it to 26 students, which is a big limitation, of course, of this course. And they always have, over those 14 weeks, always 2 hours lectures first, and then immediately after that they have 2 hours of lab sessions where we either do hands-on things related to the current topic, or they go over to the lab and work on the paddles from about the 4th week of the semester. So the goals, what we'd really like them to understand this interaction. Some of them have a mechatronics focus, so they already have the systems approach, but limited to mechanical, electrical, and engineering, computer science. We want them to broaden that and bring in the human aspect as well, so human in the loop, and then to also be able to use these and evaluate the design of efficient assistive and rehabilitation systems, also again both from the engineering point of view and from the human point of view. And through the lab sessions, the goal there really is to create that tangible link between theory and practice, so between seeing what can work in theory and how does it actually look on the setup. And this is actually one of the reasons we've stuck to the capstone drive, and I will keep that because I feel that really makes the students think more about the values they put into their controller before they go on, because it's really a big pain to put it back on when it's not so. So I purposely keep it, but I'll show you that we are also using the friction drive in another application. Okay, and then so we really, this is something we struggle with. Anybody has a good idea is to go through equations in the lab. So we have this summary on the slides, and we really work them through modeling the whole setup, and then also looking more into the controls aspects. One thing to keep some interaction in the lectures. Again, I have to, as you mentioned, this is the Swiss example. In Switzerland, students are still not used to interacting, to saying something during the lecture. They're used from from the school before, that they have to listen and believe everything that they're told. And it takes quite some time to get the discussion going a bit. So one thing we try to do is these, what our teaching department calls it interactive sessions. So I give them a picture or a video. The Cyberclown has helped us really a lot there, where we have this competition where you can show videos of what can be done with different assistive devices. And you have to look at this, but not from, you know, how much battery or how big does the battery have to be or how much torque does my motor need to have, but more from a human factors point of view. So I give them 10 minutes of preparation just before the break, so they were allowed to continue during the break. And then during 20 minutes, we collect input of what they think are important human factors if you wanted to go about and design such a robotic prosthetic hand. And then I grouped them without telling them first what the categories are. I grouped them into different categories. We discussed this during about 20 minutes and also try to take out all the stuff that's relevant for further when you actually want to then decide about a concept and which components you'll use. So that's something we use to make it interactive. And then, of course, the hands-on part is really important, that we try to keep and maintain throughout the whole lecture, not only through the use of the paddles, but we start off in the first class, we just bring all the devices we have in the lab, Falcon, an Oven Falcon, a Phantom Omni, and then Patrick Helmer, who gives a guest lecture he's the CEO of Force Dimension, brings along an Omega, so they have devices, you know, at 200 Swiss francs, 2,000 and about 20,000 to compare with. Also the kinematics I have to look at and the feeling. And Patrick shows them all the different applications they are pursuing in rehab and surgical robotics for the control. And they can try out that device. Then we do a human factors lab where we try to freak them out a bit, have them do things like the rubber hand illusion. We have mirror box. We have all kinds of size weight, color weight, temperature weight illusions, comb illusion. Vincent has that beautiful paper of all these things you can do, so that they really have to think a bit more about how they work and how what they take for granted sometimes can easily be fooled. We also take them to the lab and we do hands-on demos where we show them the devices we are developing, for example, this lower limb exoskeleton. And that's all throughout the lecture. And we have the labs then, which are every week. So from the 4th week on, we do these labs directly following the classes. And there they have hands in as well. That's all predefined, what they have to hand in when. And then the last 3 weeks, actually, they have a specialization project. And I'll get more into that right now. So the first part, we really walk them through. They all do the same thing. They all get the same hardware. We walk them through hooking up the sensor, reading it out, processing the signal, talking to the actuator, and then implementing some real-time control, also some characterization. And then the last 3 weeks, or the last, 3 weeks before the last one, they split it up into groups of 2. So we have 13 groups that will work during 3 2-hour labs, plus they have access over the weekend on dedicated hardware. So we slightly modify, split up, and give them a bit different hardware. So standard, they all have a Hall effect sensor at the output, and they have a DC torque motor. So we give them, some of them will get different acquisition hardware, some of them will get a tachometer in addition to the Hall effect sensor, an electro-optical encoder with a much better resolution. Some of them will get 4 sensors. We started off using these piezo sensors that were put in there, but now we have strain gauge-based sensors that we give to certain groups that then work on things like admittance control and using force feedback as well. And from there, they work on different topics. If you're interested, there's a list in the paper I had before of all the topics. You can also find it all online, what we provide there. And from there, they work in these groups of 2 in this computer room that we have. That's also a bit of an issue. We don't have a dedicated room. We have to move in and out of a room that's provided by the department. They get help from assistants, the people from the lab. Pretty much the whole lab is involved. And they bring in, they coach the teams on the topics that are relevant for their PhD. And then following that, they have presentations. The last 4-hour block, we put it together. They have 10 minutes, 8 minutes plus 2-minute discussion presentations. And then in the last 40 minutes or so, we move over to the demo room and they can all try out each other's demos. And here are just a couple of videos of the things they do. So there's here using Kalman filter with an IMU that's included for velocity estimation, EMG control, teleoperation, and then there's a whole bunch of advanced controls topics as well that can work on. In terms of evaluation, I also put a couple of points here that I think are really relevant or what we are trying to achieve, and that seems to work for a big part quite well. so that they really feel that the exercises are helping them understand and apply the material from the lectures. So the two are always as strong as possibly linked. Also, overall satisfaction is quite good. I try really hard to, and everybody that's helping teach is trying very hard to motivate the students to participate. And as I mentioned, this is really in Switzerland still a big challenge, I find. And this is just to show you that I also very much enjoy doing this. It's really something that's very close to what we do, and we really have a lot of fun, but it's a huge investment. The whole lab is pretty much involved throughout the whole semester. Generally, all the ratings are over 3.9, this way above what the department has on the mean. We're really happy with that. Some selected comments, of course I cherry-picked these, but some of the things, of course, we like to see. Lab's a very good link between theory and practice. Finally, something practical. There is a colleague now that does practical work already in the first year. I'll show you in a second why that is such a big challenge. I think this is also pretty much saying that it's helping, so transfer from one to the other. And of course, you're always happy to see these kind of things. There's also critical feedback, mainly that right now we don't have a script. We just give out the slides, so that's something definitely we can improve. There's also a lot of work to do. There's always some criticism on, how wide you make this, how many different things you look at, whereas how deep you can go with it. Also in contrast to other lectures they have, and also the dedicated room. So I know a lot of the labs in the US have these very nice mechatronics labs where you can go in and do these kind of things. We don't have that. That's definitely a limitation. And just to close off, so this is dedicated 26 students. We have another lecture where we get worse ratings, so I'm not just giving you the good stuff, which is a really tough one because it's biomechatronics for this new curriculum we have in health science and technology. These are students who get very little engineering background, but they are at ETH, so they need to have engineering background as well, but they get a lot of biology, chemistry. There used to be, so one of the tracks is movement science, one is neuroscience that comes out, one is medical engineering at the master's level. We have 140 students, and there it's really challenging. We cannot have enough paddles, at least right now we can't do that. So what we've done is we've made this bigger paddle. You can tell from the hand it's quite a bit bigger. We put that down at the front of the classroom, and we use it in doing a lot of demos, doing in class, for example, PID tuning. So one of the students has developed this nice interface where you can start with just a feed forward command, and we make them think about how gravity is affecting this and how it would vary if they change the set point, and then go over to PID tuning where we really tune the controller together with them, and they can see when it goes unstable or what the different components, what effect they have on the error. And this is all animated in real time, and we can try to draw some conclusions from that. Okay, so with that, I'm probably already over time, but that's so the discussion points. I think they really relate a lot, and there are more questions than answers actually, because we struggle with this a lot as well. Of course, the main point is the required resources and the resources you invest versus the benefit. So with we've shown you from the basically a trade-off between how much you can offer and how many students can profit from it. How does this scale? That's a huge challenge. Then maintaining, of course, the hardware. For this engineering week specifically, it's really for them first time learning by doing. I think this is called throwing them into the deep end or something. In real English, we call it throw somebody into the cold water, and they just have to figure out how to swim and get back out. That's a bit how they feel, and I think that's a very good experience for them, because when they come to ETH, that's usually the first year. That's what students struggle with most. They have the positive aspect that they can always bring in something creative, always build a device. There's always something to learn from that. But of course, there are limitations what can be achieved with the kind of hardware we provide. And this is really specifically addressed to this audience. It wouldn't be deep enough to provide for the university students. For the two others, I think the main challenge, especially for this PR course, is not only preparing the hardware first, but then maintaining it. In contrast to this, where we can take old components and keep them for many years, here we have to keep updating a bit, bring in new things. We've seen before the MyRio, for example, that came out. We now also have one specialization project where they can use an embedded controller, a real-time target for that, so we keep updating it a bit. And then the real challenge, so in Switzerland there is no selection of the students that get admitted. When you have this Matura degree that Olivier mentioned, you're entitled to go study whatever you want. So mechanical engineering at ETH is now at around 450 to 500 new students entering every year. And I wouldn't want to do a PHI class with paddles for all these students, but there's a colleague that's trying to do some more basic mechatronics stuff for them. We typically have, I'm always happy about that, not especially for the students, but of course for the course we always have about within a few minutes we have 40 to 50 students on the waiting list and the whole course booked out. Questions, can we select them? That's also very limited in Switzerland, what we're allowed to do there. Have them apply and then really base it on selection. And another challenge is also these students who have less of an engineering background. They don't have all the controls lectures before. And there, I think, just bringing this in, they can also come down in the break, touch it, play around with it when we have different controllers implemented. I think that's definitely something positive, but it's no way to reach 140 students. And I think especially these guys here are in dear need of actually having hands-on experience as well, because they don't have all the concepts as well established as the engineering students. So with that, I'd like to conclude here. Thank you for your attention, and I believe we have some time for discussion later on.
Yeah. So, forgot to mention at the beginning, I think while we're changing out speakers, if you have like a really specific question for the previous speaker, that'd be a really appropriate time for it. But otherwise, we'll have about 15 minutes at the end of each half to have like broader discussion. So, just, choose wisely. So, all up. Looking for the HDMI?
Oh, actually, yeah, do we have HDMI?
Yeah, HDMI is right over there, maybe on the floor. Yeah, perfect.
So thank you, Chad, for inviting me to speak on behalf of my advisor, Dr. Borowitz, who's currently attending an NSF PI conference, so she's sorry she couldn't be here. But my name is Trevor Smith. I'm a graduate student at St. Louis University, getting my master's. I'm about to finish up. And today I'm going to be talking about the Haptic Paddle, more Haptic Paddle talk, but as a teaching tool in system dynamics, which Chad alluded to earlier. And my hope is that this story will help address some of the more open questions we have about haptics as an educational tool. And I'll talk more about those at the end. So let me first address motivation in the context here. There are a lot of teaching challenges in engineering, and I'm sure that's not news to anyone in this room. And students are taught theory, which they're expected to apply to real-world problems. And there's also a desire to develop students' intuitive understanding of problems. And that can be a little bit more nebulous, and I think it's in this realm that haptics has a role to play. So, but demos and hands-on activities can be difficult to do with limitations on time and money, and it's only exacerbated by large class sizes. So this issue is particularly salient in a system dynamics course, which is a core mechanical engineering course, which all students are expected to take. Students are learning about these dynamic systems despite having little to no physical interaction with the systems they're learning about. And so this is where the Haptic Paddle comes in. So I'm going to be talking about the hardware of the Haptic Paddle a little bit here first. The Haptic Paddle, in case you don't already know, is a 1 degree of freedom force feedback joystick that lets students actually feel the forces back on their hand. And then, so they can feel the behavior of a dynamic system that's being displayed on a monitor. And here's a video of that in action. The Haptic Paddle allows the user to command a position, and then they can feel the forces back on their hand based on the position and the velocity of the paddle handle. Now, the Haptic Paddle is definitely not a new device. It's seen a lot of iteration over the past 2 decades. It was originally developed in the late 1990s at Stanford University and has been rapidly adopted by many other universities. And I'll name just a few here. The University of Michigan, they built some custom motors with a direct drive transmission. At Vanderbilt, they redesigned the hardware a little bit, and there was an emphasis on ease of use and robustness for students. And in light of this, they also redesigned the electronics and the hardware to be more transparent. And I'll talk more about that in just a bit. But Rice University, ETH Zurich, University of Utah, all had their own designs, but none of them really changed, the core of what the paddle is and what it does. So now on to the work that was done at Vanderbilt. This was spearheaded by Dr. Borowitz, Dr. Jenna Borowitz, and she contributed to the evolution of the paddle in several key ways. The design is pretty similar to that of Rice and Utah, with the inverted pendulum design, and it's powered by a motor at the base. They used a $6 analog magnetoresistive angle sensor to provide input back into the system. And this, they found, was a little bit more reliable than the Hall effect sensor used in previous designs. And all the software control was done in MATLAB and Simulink. So this provided a pretty transparent operating environment for students working in the lab, because a lot of mechanical engineering students already had experience with MATLAB, at least at some point, and they could actually kind of dig into the software a little bit without having to mess with C executables, which were used in the previous design. And then instead of using a capstan drive, they implemented the friction control using just friction drive, for the force control using a friction drive. And they found that this was helpful for the sake of robustness, so it didn't break quite as easily. Now I'll talk a little bit more about the drive change and kind of the philosophy behind it. So this is a teaching tool designed to be used in a classroom. There were several produced, and many students were using them in the lab sections. And the capstan drive offers great haptic fidelity, but the problem with it was if students messed up and they caused the system to go off balance, then the cable would lose tension. They had to retighten it. There were lots of hardware issues associated with that, and lots of time was spent by TAs and students just kind of troubleshooting. And so they really wanted to get to the core of the lab content without having to worry about so much troubleshooting. So that's why they implemented the friction drive. And the friction drive definitely trades off a little bit of haptic fidelity for the sake of this robustness, but no practical reduction in learning was observed on behalf of the students. The force data was collected using both designs, and this was fed into a Coulomb plus viscous friction model. And they both have pretty similar dynamic parameters, and these are all on par with commercially available haptic devices like the Phantom Omni. So I think I'd be remiss in continuing with this discussion without talking a little bit about the evolution of the haptic paddle as it is now. And the Hapkit, which was developed in 2012 by Dr. Allison Okamura and colleagues as a way to implement the haptic paddle for more large-scale educational projects and outreach activities. So this involved another redesign of the hardware. It incorporated a few things with lessons learned from the past. So this has been a really great example of, I think, how iterative design has been helpful in shaping curriculum. So they flipped the joystick, and the joystick configuration was just like at Rice, University of Zurich, and and Vanderbilt. They used a friction drive and also implemented a force-sensitive resistor to provide force data back into the system. And this was all integrated into an all-in-one controller board to reduce cost even further, and that's called the Hapkit. And the design costs less than $50, and it's being used for physical and online courses. So it's pretty cool stuff. So now I want to move on away from the hardware a little bit onto something that Dr. Borowitz is particularly interested in. And that's on, is the haptic paddle and other haptic devices, are they an effective teaching tool? And if so, how can we measure this? So beyond the potential benefits of engagement and excitement on behalf of the students, do the haptic paddles actually facilitate this this focus on intuitive learning? So just kind of learning about systems and understanding how they work at the intuitive level. So this was analyzed in the context of a systems dynamics course, which I alluded to earlier, and the lab curriculum itself It was divided into 5 lab sections, so each, so a systems dynamics course that had a lab with, that met 5 times a semester. And the lab curriculum itself was pretty similar to that which was developed at Stanford and Hopkins with slight modifications. And I'll kind of go into the labs really quick so you can see what they were all about. Like I said, there were 5 labs. The first 2 labs were focused mainly on the paddle components, the hardware. So since we used this friction drive, the paddles were very easy to assemble and reassemble, or disassemble and reassemble. And so the first lab was focused on the motor specifically and doing a motor spin down test and getting students acquainted with the motor. The second one, they analyzed the panel handle itself, found its moment of inertia via a bipolar pendulum experiment. And the third lab, they focused on second order systems, so like a second order undamped system, and actually, feeling the forces involved with that, with the paddle handle. And the fourth one, they touched on a topic that isn't typically covered in a systems dynamics course, and that's on PID control. So they messed around with that a little bit within Simulink. And in the fifth lab, they set up a mass spring damper system, and they analyzed some of the vibrational modes associated with that. I'll go ahead and play that video. So the labs sound great in theory, but researchers wanted to really analyze the perceived, so we think that these are going to be beneficial, but they wanted to kind of dig deep into that, into the perceived benefits of the labs, the lab curricula. I'll keep playing my videos. So in order to do this, they conducted a formal assessment, which took place over 3 years, and this was implemented in the Systems Dynamics course at Vanderbilt University. Now, the assessment consisted of 25 multiple choice questions that emphasized the core concepts that students were expected to learn in system dynamics. And the 25 questions were chosen by a panel made up of TAs who had been part of the course for several years and by a professor who had taught the course for several years. So that's how they chose the questions. They emphasized the core concepts, like I said. Students took the assessment at the very beginning of the semester, having no knowledge of system dynamics. And then they also took so that was the pre-assessment, they also took a post-assessment at the very end of the semester, and this was just to see if the students were learning these concepts at all at some point. And then the researchers also wanted to know when they were learning these core concepts and how they were learning them. So to do that, the assessment was broken down into 5-question quizzes, and each 5-question quiz consisted of questions that were relevant to one of the labs. And so there were 4 sections of this particular course, and each section differed only by when the quiz was administered. So there were 4 different time points that were analyzed. One was at the very beginning of the lab, so this analyzed how much students were learning in lecture alone. One of the time points was after the pre-lab lecture, so analyzing sort of both lectures. And these are all cumulative, by the way. Then there was a group of students that took the quiz after they completed the lab to see how effective the labs were in reinforcing these core concepts. And then after lab turn-in to see if students retain the concepts, after having had time to reflect on the lab and to do a formal lab write-up, which usually was due 1 to 2 weeks after the laboratory exercise. So here's a little summary of some of the results. As you can see, everything that's displayed in green is good. It means there was a significant increase in quiz score from the pre-test to that particular time point. And this is from paired t-test, and it also signifies a moderate to large effect size. So as you can see, the cumulative is pretty good, all except for lab 1, there was a significant increase in quiz score, which makes sense over the course of the full semester. But what I think is really interesting is after the in-class lecture, there's only 2 particular labs that the quiz score increased. And then you see that number jump up considerably in the pre-lab lecture and lab exercise portions to the point where it looks like the labs had a pretty significant effect on the material, on reinforcing those core concepts. So, in an effort to disseminate the Haptic Paddle and the associated labs, the MedLab website at Vanderbilt includes a list of materials for how to build your own Haptic Paddle, and includes all the lab handouts that were included within this study, and all the simulation files, which, like I said, are MATLAB and simulating files. In collaboration with MathWorks, they also created a 25-minute webinar. So this just describes the paddle and lab assignments in detail. So if you're interested, please check this out, and feel free to email Dr. Jenna Gorowitz with any questions you might have about that. So there are some key takeaway points, I think, to be discussed. And so to briefly summarize what was learned from the formal assessment, the Haptic Paddle appears to enhance student understanding of the core concepts, and that can be seen because only, like I said, 2 of the 5 quizzes showed significant improvement after the lecture alone. They also appear to enhance student retention of the material, especially in labs 3, 4, and 5. And the formal assessment was useful for educators because it gave them a way to assess what was and was not working. So, as I mentioned earlier, Lab 1 was the subject of some improvement because it was found that students had a tough time with those concepts associated with Lab 1. And so that was the focus of some change. And so this can be useful for educators who are trying to improve their curriculum by doing formal assessments. So as I mentioned, that's the MedLab website, and all the information is available there. Now, looking to the future at St. Louis University, Dr. Gorowitz is now faculty at SLU, and she's interested in implementing the Haptic Paddle in both teaching and research. So there are plans to contribute in several ways. One is to integrate the Haptic Paddle into a mechatronics course. Which would have been great. I took mechatronics at SLU, and having this kind of exposure, I think would be fantastic for students. And there's also plans to explore some K through 12 adoption of the paddle, especially in physics, and possibly to make it adaptable for use with the hobbyist market. So the hobbyist community has, they can do amazing things, and I think it would be interesting to see, where they could take the paddle and what we could learn from the iterations that, and that just goes along with making all this sort of more open source and available online. So there's also plans to expand into the mobile space by developing a Haptic Paddle app available for Android and iOS, and so stay tuned for that. We have a new student starting this summer who's going to be working on this, so that will be the primary focus of his work. So I'd like to leave with some of the more open challenges that this story highlights that hope feed into the discussion today. First question is, how should we assess the impact of these devices on learning educational concepts and skills? And I think there really needs to be a move towards rigorous assessment of learning enhancements, and that's pretty critical. So there's a lot to be understood about the true impact of Haptic devices on learning, and assessment's, I think, the key way to figure out what works and what doesn't, like with the first lab in this example. So what factors such as cost, technology, comfort levels, availability are important to facilitate uptake? And I think the Hapkit is a great example, the Hapkit specifically is a great example of what uptake looks like on a larger scale, make the device cheaper, more robust. And we want to expand on this idea at SLU and find a solution for making the device adaptable for broad audiences. But because ideally, the device needs and the curriculum needs to be as adaptable as possible to suit as many as possible. But I think this kind of feeds into the next question: how should the intended audience and pedagogy influence device and curriculum design? And I think there's definitely a trade-off between adaptability and lacking true content or some true specificity. So this balance needs to be addressed for any haptic learning tool that's intended to reach a broad audience. And this leads, I think, to interesting questions regarding how communities of practice and crowdsourcing can kind of take this to the next level in improving on curriculum. So the idea is to move away from having to reinvent the wheel, or the paddle in this case, every single time, and move towards leveraging the benefits of an online community that shares resources. And so with that, I'd like to acknowledge the Chrome Lab at St. Louis University, and thank you very much for listening.
Okay, this time screen. Let me restart the computer. I think it's gonna be something's messed up.
If you want, I can.
You have my
Yeah, I can pull them
Yeah.
up. Here's what I'll do.
Interesting.
Yeah. So I think the video should have to like click, accept. And
Okay.
I can get the file set. But
Perfect. So we have to turn.
so
If I click the
yeah, if you click it,
Okay.
you'll probably say like, "You sure?" And you'll say yes. Yeah. But yeah, and then if you
control that.
control, I'll let you.
Okay, so sorry for the delay. So I'm Volkan Patoğlu, and today I'm going to talk about our series elastic educational robots that we developed for physical human-robot interaction. And all credit for this work goes to my student Sata and also a postdoc at the University of Reading. What we are interested in, safe and natural interactions with human, because it's the basis for many applications, including assistive robotics, rehabilitation robotics, service robotics, haptics, teleoperation. And it's very well known that, as everyone in this room knows, hands-on experience is crucial in demonstrating engineering concepts to students. So what we strongly believe is that robust and low-cost robotic devices with force feedback capabilities are very important. They are fundamental for physical human-robot interaction education. So along these lines, there have been many works. The pioneering work is the Haptic Paddle, which we have seen a very nice introduction to in the previous presentation. So what's really interesting about this design, it's very simple, and I can't emphasize the importance of simplicity. It's also a robust and a low-cost device, and it has been, this device and many different versions of device has been used for many different lectures, including a massive online open course MOOC at Stanford University. So what are haptic pedals? What are the defining features of haptic pedals? Each of these guys are single degree of freedom impedance type devices which feature low effective impedance at their interaction port, and this is very important. So they all possess passive vectorability. You can move them around very easily because they have a low inertia design and they have a low friction transmission, typically capstan or friction drive transmission. These devices mostly rely on or can be used with open loop force / impedance control to render high fidelity virtual environments. You don't really need force sensors, even though force sensors have been added to some of these designs. And since the goal is to control the forces through the motor current, so ideally these devices need to be furnished with current amplifiers, linear current amplifiers, even though new versions, as I will mention in a minute, is used with PWM amplifiers. So there are many different versions of these devices. What we can see from this table is that the earlier versions were controlled mainly through PC-based I/O, but then the microcontrollers become really low cost. So there's more and more use of microcontrollers. Then there are two kind of trade-off decisions have been recently made to lower the cost. One of them is to use PWM voltage amplifiers. So this is a trade-off because you can't directly control the current anymore, but you use the relationship between voltage and current, and you assume that the electrical dynamics is low. And then there is the use of friction drive. It's not as good as capstan drive, but as previously mentioned, it's very good for achieving good maintainability of these devices. So what we propose is hands-on SE for series elastic actuation, which is a single degree of freedom admittance type device that features series elastic actuation. So this device has a high actuator output impedance because it uses a geared motor, with a very high gear ratio, and friction drive transmission, though friction drive is not necessary. And to achieve force control, to be able to render virtual environments, it possesses a built-in low-cost force sensor that's at the core of this device. So this device relies on force feedback and a motion control loop to render virtual environments. And the important thing is that it's not possible to render virtual environments without the force feedback. So it's an admittance type device, so you really need the force sensor to be there. The device is actively vectorable, can be made actively vectorable under closed force control, and we try to design this device such that it is physically compatible with other haptic pedal devices. And actually, it's in the sense that what you can do is you can basically change the actuator and it becomes an haptic pedal to be vectorable. And then this device uses a PWM voltage amplifier, but note that we are controlling the motion of the motor, so that's the natural choice for this device. So overall, if you look at the components of the device, the main feature comes from a cross flexure joint, which is a compliant revolute joint, which is very robust, also has a very large range of deflection that's integrated into the capstan, and the deflections of this joint, the cross flexure is measured through a Hall effect sensor, and that's it. And that makes up our force sensor. The rest is a geared motor. We prefer to use some surplus geared maximum motors, but other geared motors can be used. We have tried that work quite well with quadrature encoders. We use friction drive and capstan drive. Again, friction drive is easier to maintain, but capstan drive gets better performance. And then for the controls, we use a microcontroller. We prefer the TI Launchpad microcontrollers because they come with very nice encoder chips which can do differentiation in hardware. So you have very nice velocity signals, and they are relatively cheap, $20 to $25, and they can be controlled in real time through MATLAB Simulink interface, real-time workshop, and so on and so forth. And a PWM amplifier. Overall, the device cost, well, basically the motor cost defines the device cost is around $50 or so. And this is not really a toy device in the sense that we get 25 newtons of force at the handle. It's quite a strong device. You can come and try it during the demo sessions on Thursday. We have a sensing resolution which depends on how we select the leaf springs at our cross-flexure joint. Typical, the default sensing resolution is 0.05 Newton. Workspace is equivalent to Haptic Paddles. And then we have, of course, bandwidth limitations since we introduced this compliance. The smart force bandwidth of the device is around 12 Hertz, and then the high force bandwidth is about 7 Hertz. And here you see a kind of a high resolution version of the device, which is tracking a chirp signal between 0.2 and 0.6 Newtons. So, I mean, the performance is quite incredible. But why do we introduce this device? Why don't we go ahead with Haptic Paddles? Well, I said this is complementary to Haptic Paddles, but I really needed, I mean, for my own purposes, I needed an admittance type device in my robotics classes. So this is designed for use mainly in robotics classes where students have already taken a system dynamics class and knows controls. But they are now introduced into robotics. They have already seen how to do kinematic dynamic analysis, and they are getting into controls of robotic systems. And I closely follow Sponk's book in this controls concepts. So what he does is he first covers single degree of freedom, co-located control. Then he starts talking about joint compliance and non-collocation and position control. And that's exactly where I introduced this device, because force control is non-collocated control. It's all about non-collocation. And this device has been mainly designed to demonstrate the concepts of non-collocation, fundamental limitations of force control, and the idea of series elastic actuation to university level students. So we do this through 6 educational modules. We have been teaching this for 3 years in a row now. So the first module is pretty standard. So we use co-located control. We only use our motor, geared motor with the encoder on it. So we ask students to model the motor as a single degree of freedom rigid body system. And then they draw the root locus plus. They find out that there are no limits on the controller gains if they do P control. Then they tune the controller gains. Of course, they experience that there exist limits. So we explain why it is there. But then they do a velocity control loop, and then they characterize the velocity bandwidth of the system, and they do this for large to small reference inputs, and they see that how velocity situation actually affects the velocity bandwidth of the system. So this is kind of, they are getting used to how to use the system. The most important concept is introduced on module number 2, where we introduce them to fundamental limitations of force control. So what we explain them is, well, if you have a force-controlled system, then there will always be a non-collocation between sensor and actuator because they won't be located at the same point, and there will be some compliance in the system. So we ask them to model this compliance. Now they have a 2 degree of freedom system they need to model, and then they go ahead and draw the root locus plot of this system for a very simple P explicit force controller, and they find out that the system the root locus plus is guaranteed to go to the right-hand side, and there exists an upper limit on the closed-loop control gain of the system. So we tell them that the closed-loop control gain is directly related to the stiffness of the sensor multiplied by the gain of the controller, and then we discuss that, well, if you have a force sensor with very high stiffness, then your controller gains needs to be low. That means that your control performance will not be very good, especially to compensate for things like friction and stiction. Next, we tell them the idea behind series elastic actuation. Basically, make your force sensor gain low, then your controller gain can be wrapped up. You can get very good robustness, very good control performance, and low output impedance from this system because of the compliance. But of course, the bandwidth will suffer. And this is what we have been doing for 2 years before starting to use the hands-on AC in our classes, but it doesn't quite go through when you just explain it. So what we do next is we go ahead and make them experience it. So hopefully this works. Okay. So here they are doing explicit force control with this device, and they are gradually increasing the controller gains. And they see that the system is getting, they will see that the system is going to get unstable at some limit. And they are going to find empirically what that upper bound on the closed loop control gain of the system is. So here they experience chatter, and they are quite shocked that this happens at very low controller gains. I mean, less than 1 most of the time for the system, because they are used to the motion control and they know that they can ramp up the gains as much as they pretty much want. Then in the next module, we give them multiple different compliance joints. Here, the thickness of the leaf springs are different. So one of them is more compliant, one of them is less compliant. And, they can calculate, the good thing about the compliant mechanisms is that you can calculate the stiffness of this joint analytically with very well precision. And they compare, we want them to do calculations on what the limits of performance on the controller gain will be with different devices, and then they go ahead and empirically verify and see the trade-off, they experience the trade-off between the joint force sensor stiffness and the controller gain. And again, this is a very important module where they can appreciate the effect of the sensor stiffness on the force output or sensor resolution, as well as the stability trade-offs in the system. Then in the 4th module, we finally asked them to do some haptic rendering. First, we demonstrate them the concepts of passive backdrivability versus active backdrivability. We showed them the system is passively non-backdrivable, so nothing is on right now. So the system, there's some compliance, but it's not backdrivable. And then we turn on the controller and we show them how backdrivable it is. We even do this lace test, which they like a lot. And then also we talked about some advantages having the compliance there, like how the system behaves for low or high frequency inputs, the robustness of the systems to impacts due to the fact that there is some mechanical low fast filtering going on in the series elastic actuator. And on module number 5, we also asked them to implement an impedance control loop. So now they have a cascaded controller where inner loop is a velocity controller, then they have a force controller loop, and the outer loop is our impedance controller. So they implement some virtual environments, interact with some virtual environments. For graduate classes, we also ask them to select the controller parameters for passivity of interaction. This is for force control and bilateral calibration course, which is grad level. And finally, we ask the students to characterize the force bandwidth of the system, again for small, intermediate, and large force references. So they come up with the body plots, but this time force bandwidth plots of the system. So the bandwidth looks like this. This is for a typical device. So large force bandwidth is around 7 Hertz, and small force bandwidth is around 13 Hertz for the device. So for evaluation, we have, again, we are using this device in our Introduction to Robotics course, a senior level undergraduate course, though some graduate students also take it, 3 years in a row. And what we have done is we have asked them a question on sensor actuator non-collocation and its inevitability, its inherentness in force control in 2 years in a row when hands-on was used and when hands-on was not used. Note that concepts are always given to students before the exam, so they know what concepts can be asked for. So here we can see how well they can explain after they really experience the device, and it's double the performance. So it's pretty good. We have also done some evaluations through questionnaires, and they all find the features of the device pretty useful to explain the concepts. And one of the important features they emphasize, of course, they like the ease of use. They do really like MATLAB Simulink, because 1 year we tried with Beagle on Black, so they need to code and they hate it. So being able to do the graphical user interface, they really love it. And then we have different now versions of the device. So this is capstan-driven version, which performance is a little bit better. We are trying to work on a ball and beam, but it's very challenging because the device is not fast enough. And then this is a 2 degree of freedom generalization, which is a pantograph, but this is kind of an admittance type pantograph, and it works pretty neatly. And there is no synchronization between the motors in this very crude implementation. So, to conclude, we have introduced an admittance type educational device, which complements, it's not just alternative to haptic pedals, but we believe it complements haptic pedals and it's compatible with other haptic pedals. So you can introduce both of them to your curriculum. It's affordable, easy to use, open source, open hardware, everything is available in our website, and we have some educational modules. If you have feedback, we want to, of course, update them as possible, and we have evaluated the efficacy of the device through certain courses. Our ongoing work includes trying to introduce basically force feedback educational devices to K-12 education to promote algorithmic thinking. And if I have 2 minutes, I can quickly mention that. Okay, so I'm not going to go over this, but basically computer science is very important and everyone is aware of it. And STEM is now being augmented to STEM-C, where C stands for computing. And even though programming has been extensively applied to curricula, computational thinking is a little bit different, and it's not quite there yet. So computational thinking is the ability to formulate precisely a sequence of instructions, rules, to perform a specific task. And the fundamental principles required for this is abstraction, logic, algorithms, and data representation. These are the core concepts in computer science. And note that these concepts are technology independent. They are definitely programming independent. So students need not have computers to learn these concepts. So our idea is to introduce force feedback educational devices to K-12 education to teach algorithms. Current methods rely highly on visualization, and we believe haptic feedback will be useful because first it provides a very effective means of data hiding when we are doing comparisons, which is very common in many sorting algorithms, for example, or search algorithms. We also believe that since it uses a different modality of interaction, like haptic perception, it may result in better engagement of students. Of course, it's novel, so it's more motivating, and visually impaired students can benefit from that. So we have implemented several sorting algorithms, and during the Student Innovation Challenge, Atab and Ozan will be demonstrating this on Thursday. So this is how basically the interface looks like. So the goal is to sort identical looking springs with respect to their stiffnesses using different sorting algorithms. And the interface can provide you guidance or not, and the comparisons are done haptically. So this is what we are currently working on. We have not evaluated it yet, so we will be evaluating this on during the Student Innovation Challenge and have your feedback. That's it. Thank you.
Well, I think we're probably cutting a little into the coffee break time, but I'm fine with foregoing a little caffeine for a few discussion questions. I guess I'll open it up to that now if anybody has kind of broader things. I know we saw a lot of hardware development and some assessment now, so.
The last quick questions. When you say Cat 12, which age group are you planning to
Good question. We have not investigated that yet. I don't know. We haven't. I mean, this is kind of our goal. So we wanna. We have basically taken algorithms that's used for visual teaching, and we have hapticized them. But I don't quite know which level is the right level to introduce these concepts to students. But I know that starting from very early years, students are trying to, algorithms teaching has been used to kind of give the students a sense of systematically following a set of instructions to teach students that systematically, if you follow a set of instructions systematically, you can solve a generic problem. So they even do with very small kids where they sort themselves by, you look at the guy next to you, and if his number is greater than you, you just switch your location. So those kind of games exist already in K-12 education, but we haven't done any studies on where this is more appropriate.
I'll ask you a question, Roger, in particular. The engineering week course was really interesting. But do you think it had an effect on the gender balance? I mean, what was the gender balance with IQs? And I think in engineering we're often criticized for not being very good.
So I think first, I don't think we have big enough numbers to really look into that. And the second is also that the selection is a bit chaotic. So these are arbitrary. They have like good connections to 3 colleges who kept coming with one specific class. So it's not like we had a selected number of female and male participants. So I think it would be difficult to access that. But it's an interesting point, and we should go.
I guess the follow-on to this is your biomedical engineering. Is that I imagine it's a difference between
what I can tell you is there's a clear difference between the mechanical engineering track and the health science and technology track. So health science and technology is about half, maybe even a bit more women than men, and the mechanical is maybe 7%.
Yeah, below 10%. So to come back to your question, I think the classes that were coming were also already on the science focus, so mathematics and physics. So they, I think, already had a lower percentage of those classes.
We have one question to Oka. What's the significance of using the friction drive in this application?
It's not significant. It's easier to maintain, just as anybody else. So capstan works. They break it. Yeah, anything works.
You don't really need that.
Well, the issue with capstan drive, if they break it, it's very hard to replace. But the issue with friction drive is that sometimes there is always some slip, and then due to that, there will be some kind of the sensor.
The question is that you don't need, like you, that you don't need an extra reduction. Then you have extra reduction after the gearing after the motor.
Yeah, but we have integrated the force sensor in the capstan. So capstan is there because the force sensor is there. So we don't really need the capstan yet, but then the force output is even larger and we don't mind it. But the capstan is there because force sensor is there, and we also want it to be compatible with other haptic paddles.
So one of the questions that you were raising, Ted, was what's the importance of the device itself? So there's several different variations on devices. What do we need? You guys, Wolfgang, do you have any ideas here, or the other speakers? What do we need to create a device to make this go better? Not that it's going badly, but if you would, if you would improve your devices, what would be on your wish list? Cheaper?
Not necessarily. I think the devices are almost as cheap as they can get to. I mean, apart from the motors and microcontrollers, which you have a choice if you want, depending on the performance, producing the rest of it is already very low cost. And then if you can scale it up, as done in Hapkit, then it will be even much less cost. I think it's a matter of how much we should decide how much performance we really require for the application. And my application is very good force control, then I can, if that's the case, I can afford $100, $200 device. If my application is to show some springs, then probably a $20 device is better.
What about multiple degree freedom? Are there applications that should be from there? Building multi-degree freedom devices?
I think that's like a complication that's important, but I would say even before you get multiple DOF, I think the to me it seems like the more interesting thing would be adding these like really classical model systems. It's like giving students an introduction to strain gauge sensing or SEA, so like a SEA or ball and beam. Some of these like broader, very specific to mechanical engineering. I think maybe when you get into like haptic interfaces, that adding a DOF is a big deal. Whereas maybe on a simple robotic, yeah.
I think for multi-degree of freedom, I mean, if the application demands it, yes. But if the goal is to explain the basic concepts, engineering concepts, then 1 degree of freedom is, I think, is much better. And then you don't have to deal with kinematics and all those details, which sometimes get in the way.
Debate is basic engineering problems on the device side. I totally agree with you. If, for example, you're going to try and get it to the rendering of haptic interface, then it would be a whole different story. So, is anyone trying to teach rendering of haptic interface?
The question would be how much value is there to a Haptic Paddle, to a very low-cost device in that context, because that's a pretty rarefied context, right? Because the students who really need to learn haptic rendering are probably PhD level students who have access to other hardware. I don't know. Do you agree? It feels like the value here is that this is low cost and can be used in much broader contexts.
But I guess if C is important to STEM, then computer scientists should be dealing with rendering very simple rendering problems. And I guess why is C not put in with the N in STEM?
Sorry, why C is?
You talked about algorithmic
thinking.
Surely that's mathematics. I mean, why is there a need to have a C in STEM? Why can't you just have the M being mathematical science and computations rather than physical science?
Not exactly. I mean, of course, it is very formal and very theoretically founded, but I think algorithmic thinking is a little different from standard way that people do. We do algebra, we do calculus, but we don't really learn about a systematic way of analyzing problems.
You should learn that as well.
Yeah, I think we should learn that. Yeah, we should learn declarative programming and stuff like that, but we don't. And I think that should be a part of STEM. Yeah,
so
and I think C is not necessary.
Distinguish
yeah, exactly.
Area of computer science.
This is for the C as well. How do you detect the position of the end effector?
How do we detect the position of the end effector? So we have two sensors. So we have a sensor at the motor, which measures how much the motor is rotated. And then we have a Hall effect sensor, which measures the deflections of the end effector with respect to the capstan. And then if you add them up, you get the position of the end effector.
And is the sensing on the motor, is that past the gear transmission or before? On what side?
It's before the gear transmission. It's on the back side. It's an encoder. It need not be. It's just it's easier. And again, our microcontroller does a fantastic job of getting the velocity signal from that.
So all the presentations in the first half had some form of assessment.
Uh-huh.
There's always the surveys. Everybody likes it. It's great. But when we want to get to the rigorous kinds of assessment of education, I know we've faced a lot of challenges doing that year on year. I don't know if others have had more success or have tips or suggestions or input or perspectives on the assessment side of things. Just, I think we all sort of intuitively feel that this is a good thing to do. I think sometimes it's harder to show the hard statistics that there is some translation to to student learning.
I completely agree, and I don't quite know how to effectively assess it. And another related question is where to publish this work. I mean, we publish it in Haptics conferences, yes, then you need to go to engineering education journals. They don't like the technical stuff, they just throw it away, just their revelation. Then does it really reach the community that we are trying to reach? I'm not quite sure about that. And I see that many of them either non-published in journals or has been published in educational journals, and I think this is an open question for me. And my personal experience is not very good trying to publish in engineering journals.
I think the challenge is also that the intervention is so small compared to the rest. It's really, I think it's very similar to the issues we had with stroke training them on the assessments. The intervention is really small and there's so many things you don't have any control over. And then for me specifically, I just don't have the background also in how to set something like that up. There is some work you can get, but I think it's a major effort and then you come back to really want to put all your focus on that. It's very challenging.
When you have a large class of 40 students and you're able to do a randomized control trial.
Yes, if you get to the point where you have over 100 examples, 200 paddles.
Yeah.
The majority of presentations were using the Haptic device to teach mechanical engineering. There has been attempts to use a Haptic device to teach totally different material contents. And I'm actually involved in one of those projects, but I haven't seen many results. I'm looking at the literature. I mean, our starting point is that everybody has maybe, I'm talking about elementary transfer schools, everybody has maybe a preferred sensory modality, and somebody is more visual, somebody might be more audio, and for somebody maybe the force feedback is more important. So, and I haven't seen much done actually, so probably difficult to do because, but the goal would be to teach something totally different, not to teach about engineering, would be to teach, in our case, it would be to teach maybe geometry concepts or maybe arithmetic concepts. So that's what the project about. But what I've seen done is teaching biology, for example, exploring a cell. Somebody in the US did it, somebody else did it by exploring volumes and the relationship to volumes and area or things like that. So I don't know if there will be other talks later.
It's doing the racial challenge.
Yeah.
That's what it is.
Okay, all right. So I think because introducing a new technology in that context brings a lot of different problems because there are a lot of students. I mean, it's a novelty, it's a distraction, it's a cognitive load. It's a lot of challenge for kids to manage that might prevent learning what we want them to learn. So that's so I was wondering how you can deal when you try to teach something else that is not directly related to the device.
I'll be talking about it next.
Okay, so I should keep my questions for after you talk.
It's a great segue to the second half of the workshop. So, yeah, so I think that would be a perfect segue. And we'll go get coffee and then we'll answer these questions. Yes, thank you. Yeah, that would be great. So we've got like all the inputs you have.
I have some notes, so if you have one now.
Yeah, we got this one. Is that the display board one? That's the Mac one?
Okay. Possible to use one of the power slots?
To borrow one?
No, I'll just use power slots.
Yeah, it's not my electricity.
Okay.
Based on what you say.
Hold on, just give me 1 second. I'm gonna get through this before. Okay, it seems like it's working.
That would be good. I'm gonna, Ed maybe talk about that, and then I can try and fix. I think Jamal takes the notes. That would be good. I mean, it'll be recorded on the screen.
There we go, thank you.
Are you on procedure mode? Okay, cool.
Okay, mine works smoothly, it's just we'll just leave that there. Okay.
Wait, is it?
I was gonna see my slides.
I just finished it. I'll just change it based on what you say. Like when I was, for example, I say something like, okay, I mentioned Springsteen, but then I was like, I'm not sure, I'm just going to mention Springsteen.
Yeah, I'll sort of call it hands-on, but yeah.
Calling hands-on, okay, that's fine. I can
show you how I can show you. It's I don't think it's going to be a problem. I mean, it's not. I think we decoupled them pretty well.
Okay, cool.
But
yeah, I'm mostly talking about the design of the devices.
Yeah, that's what I thought.
And then I say briefly, because he sent the questions, I think briefly about, I just mentioned briefly Trigger Explorer and Springsteen, just because as like examples of other things you could do, but just as that.
So basically what I'm going through, and this is kind of sort of what I was thinking. We start with saying, well, this is what I'm doing, so why I'm here. Okay, and what the point here is okay, factors, so what are the game changers? What's the game? Some of them are good, some of them are like, actually, quality issue can be a challenge. And Haptic added the domain space, so actually thinking what are some of this is really where else you want to find that. I was thinking, well, there's many applications. Get some of the other dimensions of air, please. There's other things that matter here too. And so just kind of go into like, this is very good at high level, and I don't have any pictures. And then this assessing impact is something that I'm actually going to spend most time on. You wouldn't miss it.
Yeah, no, that's awesome.
Yeah, so I don't think it's, so we're kind of going through learning how to make Haptics, and whatever this talking about here, and learning about other stuff, like STEM education, and actually realizing that this is a little too black and white. Talking about like using Haptics to engineering, that I would say is sort of in between Haptics where it's already studied. And then I'm also talking about so just kind of audiences are different. Just say, okay, well, there's this other kind of teaching I'm not going to talk about it. And I'm going to focus more on other stuff. Whatever. And so accessibility, so these are things that are helping, these are problems, and this whole, like there was talking here, how the tower can really get away. Remember the power course? It's like, oh my god, we gotta get past power course. Okay, the design space, so pedagogical goals, like what are you trying to teach, hardware rendering, platforms, delivering mechanisms, and then the main thing is content development, how you're supporting content development. This is of course where we've been working with the students here. I have one whole slide on it. Okay, and then getting into assessing impact, which is, so first we try, and this is kind of the screening, so so we try to do this experiment with and without haptics, and then kind of, we did it, we didn't learn too much because it was kind of boring. And then assessing impact, and this is more what Richard's paper was, which was you're only focusing on haptics, you're having a structure, so you're doing a structured lesson. And the kids said, oh, I'm in school, and we kind of tuned out. It was like, oh, so and then we went back to really kind of a picture of what I meant by a lesson, a structured lesson. And then say, okay, so the third way we're trying it down, to fully qualitative, to say, okay, actually, you're almost like an unstructured playground. No, it's not in really trying to understand things like engagement, strategies, readings, and the language using things like that to actually understand what's going on. You can't compare it with other stuff. And so So it's a bit of a confound, difficult to do that. And then kind of going back to the defense questions and trying to get there. And that's pretty much it.
Okay. No, that's
So it's
great.
very high level.
Yeah, no, that's really cool. Yeah, so talk about what is it? Yeah, me too.
Yeah, so I mean, small education.
We're planning workshop to insurance right now. That's why they don't know. Yeah. It takes time. So we what kind of yes. No, but I mean, sometimes actually
I mean, those types of things are always shape. And of French that's actually where the test with the main problem would be probably the yes, exactly. No, I'm not involved in the whole body platform because I have to do the Haptics.
We've got time to pick up. We finish downstairs.
Yeah.
The others have got
Alright, cool. Oh, wait. She comes up and she's like, oh, your thing, it's 5 hertz. And you know, I don't know, like, I guess like on the side, people really have some like mixed stuff, but yeah, I feel like in reality, like you as a person, as long as it's cell phone and Haptics is like appropriate for your use case. That's something you can like kind of forget all that into this usual challenge state, I guess. I think if it was a PhD, yeah, and this should be pretty small. Yeah, but this is a challenge. Yeah, we're on that. We just kind of like, we really liked the API. Yeah. And the idea behind it. And the execution just was like not as easy as it was happening. Yeah, that's for us more important. For me, like the last guys on
Oh, you're trying to write it all in these drawings?
Yeah, so it has its own like graphic suite for both of them have their own rendering routine. And it's like for every time that this one runs, this one should run. But
So what's not working to draw? Drawing?
kind of every time we change something,
Okay. I think I've dealt with it. I can take a look at it after. Like honestly, I've dealt with a lot of these, but I'm using different software.
yeah, that sounds like what you said, when you run it separately. It seems to work around, it's just like different versions.
When you're trying to do the kit and happening with the same device, with the same simulation.
So we weren't able to get all three units working together. So we also were like, it's very easy to get graphics and work by itself, but we get physical device working by themselves. Getting everything together is like just not working. I think a lot of that is I don't know how to do that. Sure.
This is like one of the problems you can create tools that you try and find some of these changes, but then the simulation. Can I see it now? Very one person stuff.
Doesn't help the person who's this is good. It's like a thousand lines. So that's important. Basically, so I think part of the problem also is on started with the pixel flow approach and the one by one the Happy code. And I think what might have been a better idea was to keep the Happy example where it has like these different stuff and try and build it. Yeah, but I think part of that was pixel flow is far more complicated. Like it has like 10 classes this is a fast flow. I mean, I guess they're both, yeah, their own way. The Happy also has a lot of classes.
Yeah, that's for different devices. So what's the, this is the output from the.
Oh, so that's an earlier version. It's that's the device that connected.
And this is actually usually called by it's trying to draw something, while it's also trying to render something in a paper, right?
Yeah.
So if the very first time you draw something, if the very first time you create a graph object, you will just use time, right? And the timer starts to trigger every 1 millisecond. So if you have a timer trigger allows drawings that you do the first time, it'll create this basic control of that. And that's called concurrency. And you need a multiple time. I would try to access a variable that's not necessarily.
You basically interrupt the
it's like no errors, 60 frames a second, and it's like, this is awesome. And then you like, and then after that, it's like, shit, now we have a second. So some of the changes that we made in the way that we would stop working at this point. So we're going to go back and but it's so nice. So the demos work, like the one that displays the language and contact the wall, all works on. Although I think that one, so you have the board that's and I think that one of the is
That's the board.
That's great for people that if you're teacher, if you wire the board directly to it without yeah, but yes, now I'm on board. It's just like we don't but also the linkage is I don't know what it's like to teachers in the UK are grateful for well, except they clean they are teaching. Right. And very well. Every pre-Haptic is very fast. Probably give us a very specific and that's right. Start from the countries. I feel like it's different on there. depending on the speed to do it, different pressures, different sensitivity.
If you want to know I don't know how to do that. Students, so we have a barrier and we are that you actually do it. So you have your
These questions that are you seeing from which person is right?
So if you have this person goes, but I mean, one of the reasons has to be because one of these people, one of the students just talking about it really comes down to very factors. Also, how you the art. They were saying that one of the reasons for this is they did not self to use pressure. Students to make it just not see and one of the students everything's physical self, everything's stuck on and realized the whole thing self and every time you see the textbook, every time you should be trying to create it's flat, so you don't have a 3D concept itself.
But reading is better than using real objects. So you are not sorry.
I would say to my daughter, maybe doing some you did right.
Yeah.
Like building something out of the same.
Yeah, so in this case, it's just a sort of assessment. I think we were talking earlier about fractions. On Haptics with very young they increase fractions which is so it comes back to okay, so you can teach things like PID
haven't come that far.
Yeah.
I mean, like sand one and yeah. He was all sticks. Yeah. Okay. Yeah. I'll let you make that call.
And trying to see other issues that I mentioned, all together that 301 extension was done to teach something for Haptics. Yes, that's or as kids, but as it is that's what happens. It's a more that is not even actually to natural.
Just training wheels come off.
Yes, or it's all they're not really sprain getting the skill that's these are all I don't know how it's being done because it's for various theories and yes.
See what happens when you mix the constipation. Yeah, things like that.
Or the haptic device.
Hey, you ready? I think the rest of their coffee.
Well, this can be used, but it's not the same thing. It's not we tried to just we tried the geometric it's like the old-fashioned the one which is so it's a bit more so we've got a
Okay, I guess I've been given permission to start the second part here. So I believe this session is myself, and then Melissa, who is actually part of the same project that I'm going to talk about. She's going to talk about a quite different aspect of the project that I'm going to discuss, and then a third person after that. So getting into it, I'm going to, there's a lot less pictures in my talk than the other. Hopefully I won't put you too much to sleep. So what I'm really going to talk more is about what goes into the haptic simulations and what you're using them for, as opposed to the hardware and the engineering concepts that you might be teaching with them. So, so really thinking about the design space of what we're trying to teach and how we want to teach it. So some of the things I'm going to try and very briefly go over are why engage haptics in education. The main takeaway here is going to be that there's a lot of diversity of purpose, and that affects everything else you do. Factors that are game changers that are going on right now that are really changing what we can do here. And some of it's good, some of it's not so good. Think of haptic education as a design space itself. So what can we design in our tools and processes for using haptics in education, and where could we do more? And then this thing about assessing impact, which we are getting a little into discussion at the end, which I think is a really big deal. And I do not have answers for it. We just have some things we've tried, and we know a few things that don't work very well. And so interested in expanding the discussion right there, and then try and cap up with going back to some of the questions that Chad was raising. So why would you engage or try and deploy haptics in education? And so what I was hearing for the part, I'm sorry I got here late, but in the first part of the session, and what I've heard other people talk about when they're using haptics in education, tends to be more often this, which is what I call making haptics. So the job here is to learn how to either make a haptic device or learn how to use a haptic device to render something. I'm realizing lack of subtlety in what I'm saying here is that there's also a kind of a middle ground between this and the next one, which is using haptics to teach engineering concepts, which are very closely related to haptics. It might be robotics or mechanical control systems. So a simple haptic display is a neat little toolbox for teaching all kinds of mechanical control concepts and kinematics and friction and things like that that just come from the machine and understanding and controlling the machine. So that kind of falls into this category as well. And so there's device that you might focus on, environments. So this was something that I didn't hear covered much in the other people talking here. I think most of the learning you guys were focusing on surrounded the device, learning the device, controlling the device. When I've taught haptics over the years, I've also talked about rendering, about multimodal fusion. So if you're actually creating haptic percepts and integrating them with your auditory or visual concepts, using illusions, data pipelining, so having simultaneity between the graphics and the haptics, for example, and real-time control, synchronization, all those things are really important in terms of constructing viable haptic environments. Understanding human perception well enough to make those work. So what are your specifications down to it? And then interaction design, which is really where I do most of my teaching, which is what is the role that haptics plays in an application. But when I'm teaching interaction design for haptics, I'm teaching about making haptics. I'm teaching people how to use this tool to make something that people will use. Maybe that they themselves will use. Okay. Another reason is using haptics to teach other stuff. And this is where the conversation was going at the end of the last session. So for example, to physicalize hard to understand concepts, perhaps abstractions like mathematics or science, that might actually, it might have some physicality in it anyway. For example, understanding gravity, understanding Hooke's law, understanding chemical attractions. Or there might not be any forces in it intrinsically, but maybe we could physicalize it. For example, what's the difference between an exponential mathematical relationship and a cosine-sine relationship for someone who's struggling with those basic, what's an equation, what's a function? Could you use the embodiment of a physical device to actually help, for example, kids understand abstractions better when they're struggling with abstractions, make it real? So what you might do is to provide some kind of a sandbox, some kind of a toolkit that allows kids, I'm thinking of kids more often, but could also be certain parts of the university population, engage with these concepts, accessible science experiments, making things that are not physically realizable. You can break Newton's law. for example, and very quickly that Control-Z, undo and try it again. You can iterate really fast when it's done in software and a virtual environment rather than a real physical system. There's benefits of embodiment, the fact that you could have your body moving around as you're understanding it. Learning theory will tell us that that can actually be helpful, whether it could be because you're a different kind of learner or just because you're engaging more sensory modalities as you learn. And you can actually use this as a platform to study how people learn these things. For example, if you want to understand how embodiment actually helps a kid learn math, you might use a physical device, a haptic device, very productively, simply as a platform to study that in. So those are some reasons you might actually want to use a haptic display, for example, to teach people or help kids learn about stuff that's not haptics per se. So the audience for it, so I'm going to call these number 1 and number 2. Number 1 is making haptics, and number 2 is other stuff, using haptics for other stuff. I'll come back to number 1 and number 2. So when you're making haptics, usually, and I think you guys will mostly agree with me, I would say based on the first few talks and other sessions we've done on haptic eggs over the years, some STEM background, maybe not a lot. It depends on who you're talking about. Your engineering week, I think it was, maybe had a little bit, or at least they were headed in that direction, but maybe not very far along yet. Probably had high school physics, at least. Some interest, some need to learn the technology itself. There's intrinsic in this that there's a reason you're teaching them about motors and sensors and things like that. There's a reason they should learn that. Maybe they want to, maybe they need to for where they're going academically. When you're talking about using haptics to learn other stuff, it's very often, more likely than not, low to zero STEM background or inclination. Almost by definition, these are often the kids who do not have that, do not want to go there, are struggling because of that, okay? If they have to learn technology to get there, you're finished, okay? You might as well not start. They're going to be struggling so hard with the infrastructure of getting there that you won't get past it. If they have to use Arduino, just stop, okay? They don't know how to program. Okay, engagement maybe as important as what you can learn. Okay, so the fact that it's physical and that's enticing and it draws them into the experience is a confound in terms of learning what they can learn, but it also is really important if it brings them in. It's not a bad thing. And so these are really different situations. So I've done the number 1 kind for pretty much at least 20 years, over many different versions of haptic courses, ranging from hardcore engineering robotics to different ways of teaching interaction design. Most recently, I've been having a lot of fun teaching haptic sketching as a way into interaction design. And again, what's different about the kinds of courses you guys were describing earlier on is it really focusing on what you can do with the haptic feedback and less on making it. We do a little bit on making it, but it's more about sketching and trying to understand the role that haptics will play in interaction and making that real. And these are just some pictures from from the class that I teach. You can see the kinds of things like, that's a haptic device, made in 10 minutes. We have this thing about, does it take 1 minute, 10 minutes, 1 day, 10 days to make a haptic experience in terms of how far along the design pipeline you are. So I didn't actually mean for that video to play. Okay, so I didn't want to spend too much time on the haptic sketching part because I want to talk more about the other stuff. So the context for this particular story is a 3-year project that is just wrapped up that did with Allison Okamura, NSF funded, and the goal is how do you use haptics to teach STEM concepts to K through 12. Actually not K through 12, really talking about upper high school, so grade 10, 11, 12. People who are perhaps struggling with basic physics abstractions and other kinds of things and trying to get them over that hump. So Allison's lab, represented by Melissa here, was really more focused on the Hapkit, the hardware, and making that really accessible. I came in very interested in, you can't have them use Arduino. That won't work. So, well, what should we use instead? So that's what I was doing, was what should we do instead? And Paolo Blickstein is our education person on the team who's really trying to look at what the learning theory that's actually in there. So we learned a few things, and we did not learn a few things. This is actually quite a hard problem that we did not make as much headway on as I had thought we would in 3 years. So first of all, there's some things that have changed in the world over the last few years, and most of these were starting to be in place 3 or 4 years ago. Of course, they're much more in place now. So low cost, do-it-yourself open source hardware. There's now a whole bunch of different hardware devices that people have open source, not just variations on the Haptic Paddle, but lots of others. There's 2 degrees of freedom devices. There's 3D devices. All these things you can build with 3D printers or laser printers or different things. And it's not that hard to build a haptic device. It doesn't have to cost very much. People are familiar with it. Kids know what haptic feedback is. They don't think it's a liver disease anymore. Growing appetite to customize and experiment. I don't like the way my cell phone buzzes. I want to change it. Okay, well, how would you do that? And even possibilities for online delivery and other crowdsources and sharing, because so many people are actually having haptic devices of some sort that they could actually imagine that. There's some problems with accessibility. We're not totally there. And quality is one of them. Now, some of the discussion at the end of the last talk was about, oh, well, the quality is really good enough for if you're spending $100 or $200 on a haptic display to teach an engineering concept. But now, if what we're actually trying to do is go to a high school class, which has pretty much a zero budget for this stuff, and teach people not about how to control a haptic device, but to render physical stuff in a comprehensible way that they can actually feel distinctions between it, and this has to be really, really cheap, I would say we are not there yet. We need this device. Okay? Low-cost device, the cheaper you make it, the lower the quality. Typically, that's kind of the world we're in right now, depending on how low you go. And another problem that might not have been quite so obvious to everyone is that in these DIY devices, so let's say the high school students are building their devices by themselves or under the help of their physics teacher in the high school classroom, and they're using it, and let's say, I don't know, all these devices together, who's had a whole lineup of haptic paddles, do they all feel exactly the same? Can you tell when it's broken if you don't know how they work in the first place? I would say, no, you could have a kid using a Hapkit that's not strung up quite right, and it doesn't work, and no one will know, and it just won't feel right, and they will learn the wrong thing. Okay, so it's very hard remotely to guarantee or assess whether the students are feeling what you think they're feeling. Okay, so this is actually a problem. If you go for the high quality devices, they're still too expensive for this application for the most part. They're hard to maintain. It's hard to look at it and understand what it does. Omni comes with a fairing over it now, so you can't see inside. It's kind of like your car that you can't open up the hood and understand how the engine looks by looking at it anymore. And then the tech really gets in the way. You say DIY, wow, it's great, anyone can build a haptic device. But we tried to put them in a classroom, and we got stuck at the level of the power cords. Everyone was tripping over the power cords. We didn't have enough outlets for the power cords. And it just tells you that there's so many obstacles to deploying hardware in a classroom setting or in kids' homes that you just don't think about it until you try it. So this is actually we're not as far along on this as you might think when you're actually trying to push it out to that next level. And then I'll also say that not everyone actually thinks 3D printing and electronics are fun, and this might be the audience that you're especially trying to reach. I just did an outreach session at my university where I brought 60 very talented high school kids into the university and took them around, and I had 4 different sessions in computer science that they could sign up for. And I looked at who was in those sessions, and they were all the boys. The girls wouldn't sign up for them. And it was like 3D printing. There was 18 boys and 2 girls. It was just really disappointing. That the self-selection there is just not what you were hoping for. And then design tools, and this is really my pet project is what are they actually interacting with in terms of the software interface that lets them have these wonderful, engaging experiences, that lets them build stuff, that lets them learn stuff, that have the right amount of challenge versus effort, and how do you actually build those kinds of things? So if you're making haptics, these are not so bad because there's a certain level of talent, there's a certain level of specialization skill you can assume. So CAD programs, rendering engines, being able to integrate graphics packages, just look at how well the students in the Student Innovation Challenge have been able to do this, even though we say they're mostly novice haptic makers. They had enough background that they could jump on all of this stuff and do a pretty good job. But when you're talking about your high school students, we don't have that. We're starting from a very different place. Okay, so Haptic Ed is a design space. So what I mean by design space is it has dimensions. And that means that these are fronts on which we need to advance and contribute and learn. So here's a few. And I don't have time, I know, to talk about very much about any of them. Pedagogical goals, we've talked already. The previous groups really covered these wonderfully. And I've said a little bit about why you might actually be doing this, and I won't come back to that. Hardware and rendering platform variables. And that's, again, I think something that you guys have been doing great on. Delivery mechanisms and the audience. So are we talking about in the lab, in the classroom, in a university classroom versus a high school classroom? Very different online, on your own. What's the difference in the learner background? All of these things are going to require different delivery mechanisms, different degrees of scaffolding and different support tools. What kind of tech support? What kind of lesson structure? Scaffolding environments. So there's examples of all of these out there, but as soon as you make different pedagogical goals, all of these things, of course, need to change. No surprise there. But that's a dimension. Okay, ways in which content development is supported. And I feel like this is a dimension that is really getting short shrift. So content development by learners. Okay, that's one kind of content development. So if you want the learner to be able to build stuff and design stuff and make stuff and learn stuff, that's content development. By teachers who are trying to structure a lesson of some sort. And it might be very low amount of structure, but they still have to think about what is in there, what do the students have access to. How do they do that? They're not very far ahead of the students on their background knowledge of things like the mechanics and the software, okay? So it's a different purpose, but they might be very similar in terms of knowledge of the technology. Or by third-party learning content developers, so people who maybe have the job of actually creating systems that teachers can then deploy in their classroom to do this. Okay, so the other stuff audience is most affected. So remember, low to zero STEM background. If they have to learn technology to access it, it's a non-starter. Engagement may be very, very important. What goes up there? Okay, so the tools, these tools need to be accessible and engaging. So if you do Arduino and Java, that's no good. Instead, we need visual programming languages. And everyone knows Scratch, or Scratch, things like Scratch, okay? Graphical programming language, visual programming, you click on something, you can open up and look inside and see what the code is inside. I want to build that for haptics. Okay, then we have control theory. No control theory, instead we want powerful and appropriately framed primitives that students can use. And then scripted lessons. It turns out that scripted lessons are kind of problematic. I'll come back to this. Instead, we want creative design sandwiches. Let me get it. Must be that time of day. Creative design sandboxes that kids can play around in. Okay, so that's all I'm going to say about that. Okay, big open-ended problem that we're trying to struggle with a little bit. But I want to move on to another thing which we did dig more deeply into, which is assessing impact. So how do you tell if what you're doing is helping? Okay, so Marcy brought up, and all of you guys were doing impact assessments, usually through peer, not peer, student evaluations, self-reported responses. 5 to go? Yeah, okay, good. So I'm going to look at it a little bit differently. If you actually want to watch the students and see what they're doing, and you're actually trying to say, for example, we wanted to go back to NSF and say, oh, yay, we deployed haptics in education. It was slam dunk win. Look, they learn way better when you do this, like an objective test to say, oh, if you add haptics, they learn it better, faster, more creatively, more transferably than if you don't have haptics. If you have that goal, if you want to document that, what do you do? So here's one thing you could try. You could do a controlled experiment. We're scientists, we like to do controlled experiments. So let's say compare groups and situations with and without haptics, okay? There's a problem. If you design a thing really well to have haptics, then if you take haptics away, it probably doesn't work very well, okay? It's cheating. And if you design something that's designed without haptics and then you just slap haptics onto it, that's probably not going to make much difference. They're both going to be optimized in different ways. So if you try and narrow it down to a space where it seems like you can actually fairly test this, you're in a really, really narrow space that you're just kind of closed into this tiny little thing. And it may not be super interesting anymore. This is a thing that we presented at Euro Haptics last year. And this is kind of the schematic view of it. And so this is, if you're trying to learn Hooke's law, here's a thing where you can tie a haptic interface up to it. And you can say, oh, I'm feeling this spring, I'm doing this spring, and this spring. I can change all these things about this system. I can put them in series or parallel. And I can turn the haptics on and off, okay? And I can do it with and without, and I can actually do an experiment this way. I could take this little block away from the students and actually do this as a controlled experimental condition. And here's what the actual interface looked like. And yes, we actually did this experiment. Did we learn anything? A little. I wouldn't say it was a resounding impact on it. Mostly we could kind of look at what people were doing and how they were doing it. Okay, so I think our biggest problem there, though, was that we actually felt like we got so narrowed down that it just wasn't very interesting anymore. This really wasn't what we had in mind in terms of how you would use haptics. It wasn't a super compelling use case. So the next thing you could do is you could try and evaluate just the haptics part. Forget about the with and without haptics. But we're going to have a little structure. And so you're going to look at how people are using the haptics. You're really going to study this in a qualitative way. But you're going to script the lessons, you're going to structure them, you're going to take it through them because you want to make sure the students are encountering the situations that you want to study. So you need to give them that structure. It's not quite in the wild yet. And so it turns out that as soon as you give students a lesson, they say, oh, I'm in school. This is boring. And the brain turns off. It's amazing. I should not have been surprised because I have a grade 10 son. But there we were. And so we found that the kind of all the creativity we see when kids are just playing around open-ended with a haptic system goes away when you put it into a scripted lesson. And we thought, well, that's just not a way to do it. But this is really a problem because you say, well, it's a confound. The lack of engagement is not just about haptics, it's about lots of things. We bring haptics in and haptics helps with engagement, that's really great, but how do we tell if haptics is actually helping them learn something as opposed to just being engaged? And most of the time we're not getting past the novelty effect anyway. So if we actually improve engagement, what is haptic, is it helping them understand something better? We don't know. It's very hard to decouple that. And so we got a bit frustrated by this. This was another paper that has just been, it'll be presented next month at, actually next week, at Interaction Design for Children, held at Stanford. It's called the Haptic Bridge, trying to understand how you can do haptic supported learning in just this way, and they're trying to actually develop some kind of pedagogical theory here. And this is just an example of what we're looking at in terms of what's a lesson. So here's this very careful thing where you're sort of giving them some background knowledge and they're going to play around with it in haptics. So you say, the idea here is that you learn something once, and then you ask people to transfer the idea to another situation and see how well the transfer goes. And this is an accepted thing in educational research that you can actually study it. And again, I'm not talking here about how we deployed the haptics just for lack of time, but again, the problem was it looks too much like school, and this seems to be an obstacle to learning, which is a little bit frustrating. And so the next step we can try is to go fully qualitative, build something very engaging, and just forget about the science about it and try not to be scientific anymore. This is actually what we had originally wanted to do in our 3-year grant, but felt like we had to be more scientific about it. Okay, so the playground, these are some of the mechanisms you can use. Have teams, make them compete against each other if they want, or make them work together on a team project. Gamify it, use usable primitives, and then give them creative constraints that they have to solve. It may require new programming languages to actually build this environment. There's where the computer science technology actually comes into creating this thing. Then you look at what students do, and a completely qualitative kind of design with thematic analysis where you're looking at engagement, you're looking at the strategies they use, the things they're actually doing as they're working, the language they're using to talk about what they're doing, and actually understand what role haptics is playing in what they're doing. And that's the kind of research we're engaging in now. So I just wanted to come back to the questions here. So personalization of device and curriculum. Say haptics makers versus using haptics to learn other stuff, very different backgrounds. You're going to need to do different environments, different tools for both of these. And in my opinion, hardware is the block of one. Maybe that's not a widely shared thing, but there certainly is a lot of attention on designing the hardware, which is what I'm hearing. Whereas both hardware and the tools, and especially tools, are what are blocking the second kind of actually using haptics for other stuff. How much should a device cost? And I would say that if you're trying to deploy it at this level, they have to cost as little as possible. But since we can't reach zero probably, or the quality proposition will be so bad, really need to connect the device specifications to the learning goals. So what are you trying to learn out of this particular haptic concept? And understand the role that haptic is playing in there, and from there you can derive how good the haptic experience has to be in order to get that across. How high fidelity, how strong does it have to be, how many degrees of freedom, for example. We need to do better in establishing those learning goals so we can go back and specify the haptic technology. What facilitates the uptake, let's say gratifying experiences where the effort is focused on the learning goals, whatever those might be. That'll differ by audience and by the particular subject you're trying to teach. And then assessing impact is hard to quantify. Both hardware and the tools are going to get in the way. So I will stop there and move on to the next person. And Melissa will follow up talking about the same, kind of the same project context, but much more on the haptic environment that we're using.
Alright. So now as we know, haptics and movement and learning are very interconnected in the brain. One of my favorite examples of this is the fact that according to neuroscientists and education researchers, when we're doing a calculation, we actually see a representation of our fingers in our brain, even when we're not using our fingers to count. And we also know that hands-on educational activities can help students understand abstract concepts better by connecting them mathematical models to physical interactions, which is why we're better trying to understand the role of haptics in learning, and we hypothesize that a haptic virtual environment may teach students intuitively about concepts that are difficult to grasp by just seeing equations. So in this workshop, what I'm mostly going to talk about is our experiences and lessons we have learned in designing haptic devices for education that should be used in a classroom, but also in informal learning settings. So yeah, I mean, there's been a lot of talk about Hapkit, but it was mostly created with the idea of building a haptic device that should not just be a laboratory equipment, that should be able to be used by high schools. And as Karen said, we're probably not there yet, but these have been our experiences in designing this device. And so our idea was that if we're going to design a haptic device that was not to be used as just as a laboratory equipment, it should be a kit, and students should be able to not only assemble them, but manufacture them as well. So the first version of the device was Hapkit 1.0, and it was created in 2013 at Stanford University with the aim of being used in an online course for 100 students. And there were several changes made to the original Haptic Paddle, just like the ones inspired by the ones made at Vanderbilt University. And so first, the drive mechanism was changed from a capstan drive as a friction drive, which was already explained. The device was made out of laser acrylic cut by laser cutter, and the motor was a Maxon AMAX motor, which was obtained as a surplus item at a very low cost. But the most relevant change really was the design of the electronics board and partnering with Seed Studios so that they would sell it through their website. That way anybody can purchase it online and they don't depend on us to be able to acquire it. So what we did was we grabbed an Arduino Uno board, and then we just added on a motor drive circuitry, an SD card reader, and a magnetoresistive sensor. And that way, by using the Arduino Uno family of devices, then there's already all this code and community of practice that helps people debug code.
However, even though Hapkit 1.0 really was a very robust device, and it was also used at undergraduate courses in Stanford as well as in educational studies, one of which I will talk a bit, Karen touched on it a little bit, but I will talk a little bit more about it. The fact that it was made out of laser cut acrylic meant that nobody could really manufacture it by themselves because students just don't have access to a laser cutter. So then we designed Hapkit 2.0, and the main idea behind it was to use 3D printing because 3D printers are very accessible nowadays. A lot of schools, well, at least the ones we work with around our area, which might be very presumptuous, but they do have access to a 3D printer. And so, so the idea between, we had to get rid of the maximum motor, which I know may sacrifice the haptics a lot. And so, so later I will talk about work we did in order to try to not sacrifice the haptics with a cheaper motor. And so as you can see, Hapkit 2.0 kept the same basic design as Hapkit 1.0. It uses a friction drive, and you have a height adjustment bar to be able to adjust the amount of friction. However, one thing that we did not account for when 3D printing was warping during 3D printing. So if you use something like a Projet or something like that, you can print parts that are circular and they will come out circular. But if you use like a MakerBot or something that schools have access to, if you try and 3D print something circular, there will be an eccentricity larger than a millimeter, and then that's enough so that the paddle actually does not maintain constant contact with the drive wheel at all times. And so for our studies, actually, we had to laser cut the paddles. And we tried with several, not only with the MakerBot Replicator 2, we tried with a FlashForge Creator and an Athenian H480, and none of them were able to print good paddles. So we used Hapkit 2.0. We deployed it for our massive open online course. We put the instructions on how to build it online. We used it in our university and in a middle school classroom. And each one of these educational settings gave us different ideas on what to improve on it. So first, as Karen mentioned, in a massive open online course, it's practically impossible to try and tell students what the right field should be. And so having a device where you have to adjust the amount of friction just for them to be able to use it was definitely a no-go. In the university course, we had the advantage of having instructors being able to walk by and tell the students, yes, this feels right, yes, this doesn't feel, no, this doesn't feel right. But yeah, we can't do that if we're gonna do online or in schools. And then also over 2 weeks in May of 2015, we ran a pilot workshop at a middle school with 32 students. The course was a modified version of our MOOC and freshman course, in which students were giving a brief introduction to haptics and how the Hapkit works, and they were aided in rendering a spring, a damper, and a texture. So in this scenario, the students, they were middle school kids, and they did not have to build the devices. We brought them already assembled. But then still, even though they were already assembled, the younger population stressed the devices in ways we would never imagine. Like they knocked them off of the desk, they broke little pieces of the 3D printed material, they would try and screw and unscrew the Hapkit board. And so they also would press so hard on the handle that just the drive transmission would just shear off. And so, yeah, they were still enthusiastic about it, but we knew we needed to improve our design, make it more robust if we were going to keep doing this. And that is how Hapkit 3.0 was born. The first thing we did was design it specifically for 3D printing. That's why we changed it to a more rounded design, because rounded things just print way better and with less warping in 3D printers. We also added suction cups so they would stick to desk so that students couldn't knock them off. And then we made a snapping mechanism for the Hapkit board so that it wouldn't have to be screwed in anymore and the parts wouldn't like break apart. You just put it in. And also, we took advantage of the customization that's possible with 3D printing, and so we designed the whole device in two different parts. So the bottom part is the functional part, which students should not alter. But the top part, the handle, students can design their own handle. And we went back to the capstan drive. And so what we did is we focused on trying to make a capstan drive mechanism that was easy to assemble, and that wouldn't, even if the device would become unstable, the capstan wouldn't like come out and you wouldn't have to assemble it again. And so what we did is we added like a slot for fastening the capstan cable, so you will tie it around, and then with a slot you will just push it in all the way as far as it can go, and that gives you the right amount of tension. And then also, in order to prevent the cable from unwinding, we added a stop at the drive wheel so that it won't come off. And because it has a neoprene tube, when you wind it around, it compresses the neoprene tube, and that also prevents it from moving around. We've used Hapkit 3.0 in graduate haptics classes, and undergraduate controls class, and undergraduate introduction to haptics class, and dynamics classes. And also in an undergraduate seminar that Allison taught in Kyoto, Japan, which I will talk about a little bit in a bit. And throughout the teachings of these classes, we made one minor improvement to the design, which is important. We changed the printing settings for the drive wheel so that they print at 100%. So usually a low-cost 3D printer will print things in layers, and these needed to not be printed in layers, had to print 100%, so nothing would shear off. And so one thing that we did not expect from Hapkit 3.0 was learning just how important it was for students to be able to customize these devices. We really thought that giving them customization would just be kind of cool, but it turned out to really give students a sense of ownership over their designs and learning. And so that inspired us to see, okay, then what else can we turn these devices into? And so what we did is we came up with two degree of freedom designs, which are showcased in a paper and demo, which here at the conference. And the first one we call Hapkit. And the idea behind these designs is that hopefully students who use the 1 degree of freedom device and learn 1 degree of freedom concepts can then later transform those devices into 2 degree of freedom devices and then learn 2 degree of freedom concepts. And so the way Hapkit works, as you can see, it uses a pantograph mechanism, and it just adds a few parts, so it adds a cost of about $10 per kit to the Hapkit. And so in the undergraduate seminar that Allison taught in Kyoto, it was really interesting because students built Hapkit 3.0s and learned about haptics and dynamics, and then turned those Hapkit 3.0s into graph kits to learn the dynamics of the pantograph mechanisms. And the students were able to use these devices both as drawing robots and haptic devices. And this class was particularly interesting because the students at Kyoto were not engineering students. Some of them were, but a lot of them were history majors and just they were not engineering, and they were all able to complete the course. Allison did say, for example, that the non-engineering students were very scared at the beginning to building the devices, but I think the fact that they were mixed with engineering students and they would help each other out really engaged them into doing it, and she said everybody completed the course very successfully. Now the other 2 degree of freedom device we called Haptic. And now for creating Haptic, what we did was we decided to customize Hapkit even further, and we allowed ourselves to modify the parts. So we increased the angle of rotation of the sector pulley in order to allow for a larger workspace. And then Haptic is composed of 2 Hapkit sector pulleys with modified handles now connected in a series mechanism, which allows both motors to be grounded by a modified base and suction cup mounts. And now what's cool about the serial mechanism is it allows it to have very simple kinematics that fall directly from the 1 degree of freedom device, which we're very excited to try soon. And then also, unlike other serial chain mechanisms that use pulleys or cables that apply off-axis torques on the motors, Haptic allows a direct transmission through capstan drive, which allows us to be able to still use our not so nice Mabuchi motors. And so, so far, the devices have been mostly used as hands-on activities to ground dynamics, physics, or haptics concepts. One of our goals, however, is to be able to use haptics to teach other concepts that may not intuitively be related to the physics of the devices themselves. So Karen mentioned about Spring Sim, which hands-on, a program in which you can use haptics to give you hands-on experience on how to manipulate springs. Another very cool application that we have found is actually in trying to aid students in linking 2 very abstract mathematical concepts together. In this program, for example, students can interact with trigonometric functions and the unit circle. Using Hapkits, a student can feel a mathematical function. So as you're going through it, you can actually feel the function, as well as see the effect that has on the unit circle. And they can change the amplitude and the frequency and feel the differences. This wasn't super stringent. We ran a 4-participant study, so we ran 2 different sets of high school students through this. And we did see, but this is just observational, we did see some promising results in the students learning to graph these functions after feeling them. But of course, we need to do a lot more work in assessing whether this is true or not. Now, the other set of work that needs to be done when designing these haptic devices, we believe, is that you imagine that when you try to teach these lessons, it is very important to understand the rendering capabilities of your devices that you're using. So if you're going to teach something about springs, you really need to understand which types of springs the kids are going to be able to feel. So the first thing we did to understand our devices was use a linear model to describe the dynamics of the structural components, and we quantified the difference between the three Hapkits. Then we used the frequency-based method where we input torques, just very similar to the one run by Rice. We input torques and measured position to fit the parameters of this model. Now we can see, which is very cool from the results, that Hapkit 1.0 and 2.0 have a higher damping coefficient, which makes sense since they use a friction drive, and Hapkit 3.0. The inertials of the three paddles is very similar, which makes sense. They all weigh about the same, except Haptic 3.0 is a little heavier, and the mass is mostly concentrated around the edges because of the 3D printing process. And so now that we have a model of the paddle's mechanical components that we can correlate to, we wanted to understand now people's ability to discriminate virtual spring stiffnesses of different springs using the three Hapkits. So we performed a stiffness discrimination test with 14 people using a force choice paradigm with the method of constant stimuli. And the experiment was divided into 3 sections, one for each Hapkit, and a computer program chose at random the order for each participant. Now for each Hapkit, a participant had to make 100 spring comparisons. There were 10 different spring pairs, and each spring pair was compared 10 times, which was pretty brutal, but the participants were bribed with cookies at the breaks, and they went through it. And so after gathering all the data and finding a just noticeable difference, and then from there the Weber fraction, we found some interesting results, which are that for the Weber fractions for Hapkit 1.0 are 10.5%, for Hapkit 2.0, 11.5%, and 6.1% for Hapkit 3.0. And then a two-way ANOVA test also revealed that Hapkit 2.0 is statistically different from Hapkit 3.0 is statistically different from the other two, which is also very cool to learn since it's the one with the different drive. And now these experiments and fits now then give us guidelines to aid us in designing which environments could be used in a variety of educational settings. And finally, the reason why we do all this work is that we believe that the potential for haptics in learning is still very much untapped. We still have to work a lot in how to assess these, but we hypothesize that students can gain, just like with any other language, they can gain intuitive understanding of many concepts using haptics. Thank you.
Yeah, exactly.
It's just
I've got a little video at one point. I hope it will pick it up. I've got a little video at one point, so I hope it might.
okay, that's
HTML.
that's right.
There we go. So, hello everyone, thank you for coming. My name is Megan Tracy and I am a PhD student at King's College London. And thank you for coming to my first conference talk, which is Reimagining Biological Cells, Evaluating 3D Learning in a Cooperative Haptic Environment. So I'll start by giving you some context a little bit about the projects I'm involved in. So the project is funded by the Legal Human Trust, and it aims to examine whether 3D haptic-enabled virtual environments could enhance learning by providing visual and haptic feedback and providing students with the opportunity to explore through natural manipulation and cooperative learning. So collaborating on this project, we have a multidisciplinary team from King's College London, University of Reading, our industry partners, Gaia 3D, and our partner schools, the Abbey and Abingdon. So designing this project, a lot of discussion was had about what kind of topic would benefit most from 3D visual and haptic information, and we came to the conclusion that cell biology was a great candidate for this. So I'm going to tell you a little bit about the problems with learning cell biology in secondary education and how a 3D haptic approach could help. So what are the problems with cell biology? Well, cell biology is known to be a particularly challenging subject due to its complex and abstract nature. This is evidenced by the numerous and widespread misconceptions at all levels of education in biology. The literature shows that concepts like diffusion and randomness in the cell are consistently misunderstood, despite them being pretty critical in understanding the cell. And also the abstract and unobservable nature of cell biology prevents students from directly exploring these concepts, which is a strategy that's important in science learning. So many of these misconceptions come from the representations of cells that students are exposed to. So a lot of them are textbook cross-sectional schematics or light microscopy, which you can see here. But they're really limited in their ability to realistically represent the cell, and they've been shown to support prominent misconceptions. They are quite abstract. Another barrier to effective learning in cell biology is the need for visualization. So with students unable to directly view and manipulate these structures, understanding on the subject relies on the ability to visualize them, the structures, the systems, and the processes at the molecular level. Visualization is known to be an important cognitive skill for understanding structures and processes in science generally, but is especially important for understanding cellular processes due to the need to model abstract and complex information. So these are just a couple of representations that students get shown to do with cells, and all of them are pretty abstract. So taking those pictures and turning them into a realistic depiction of the cell in your mind is quite difficult. So understandably, it results in the lack of understanding and misconceptions that are demonstrated in classrooms. And the lack of understanding in cell biology is particularly problematic because it's quite critical in understanding biology as a whole, and it's the building blocks of biology. So with visualization being critical for science learning, the high demand for visualization in cell biology presents issues for students with low spatial ability. So people with lower spatial ability might find the content difficult to conceptualize without direct observation. And acquiring these skills can often be difficult, and despite demonstrating surface level knowledge, a lot of students show that some of the fundamental concepts they don't quite understand. So technology-enhanced learning might be a useful approach, including the use of animations and interactive websites. However, evidence is mixed at the moment, and it's been suggested that the use of animations, for example, may even add additional barriers to learning. More recently, 3D and interactive software and models have become available. For example, 3D projectors can now be used in classrooms to demonstrate cut sections of cells, like the little picture here. But the representations are still very stylized and unrealistic, and educators have continued to report a lot of misconceptions despite using them in their classrooms. So the literature suggests that a cell simulation, which allows students to actually manipulate and observe cell processes, might help reinforce specific educational concepts. And there's also evidence that haptics may be beneficial for this. So haptics can enable the students to directly manipulate the object, which is previously inaccessible, and allows physical manipulation of an unobservable phenomenon, something that is usually unobtainable in a classroom. So this physical manipulation is known to be beneficial for learning in other areas of science, so to be able to mimic this would be quite helpful. So the evidence for the role of haptics in science education has been covered by 2 reviews so far, both finding mixed results. So the first one was by Logan Jones, who concluded that haptics is a positive addition to science learning, especially when visual information is inadequate, as with cell biology. They also concluded that more research is needed to assess the role of haptic feedback and how to best implement it in education. So this second review is from Zachariah, who compared virtual manipulatives with and without the provision of haptic feedback. And again, they also found mixed results. And although most of the studies found a difference, there were some in there that just found no difference at all. And similar to the previous review, Zachariah concluded that it's reasonable to assume that haptic feedback has some effect on learning in science, but it's especially so for abstract concepts where visual information just isn't available. So, why haptics? So there's some theoretical support for the potential benefits of haptics in science learning. So multimodal learning has been shown to be advantageous compared to single modes of representation. And the addition of haptic sense to the visual and auditory information traditionally provided in multimodal learning presents an opportunity to further support students. Further evidence would come from dual coding theory, which suggests that there are distinct systems for different sensory modalities that work together, allowing the beneficial effect of combined coding of sensory information. So dual coding theory traditionally refers to visual and audio information, but according to this theory, the addition of a haptic sense would work synergistically with other sensory modes to aid the coding of complex information. Related to dual coding theory is cognitive load theory, which suggests that the excessive cognitive load, which is information waiting to be processed, can be alleviated by using multiple modalities and their respective separate processing channels. So according to this theory, the addition of a haptic sense to a learning experience may lower cognitive load by utilising a separate processing channel, allowing an additional method of processing the complex information, such as that found in cell biology. So for this project, we've conducted 2 pilots already. One exploring the usability of the technology with 6 biology undergraduate students, and another piloting improved technology and relevant assessment methods with 30 students aged 16, 17. So I'm going to explain this briefly, but if you want some more information, the paper's at the bottom, have it there. So our first pilot, students undertook an activity in pairs exploring a virtual plant cell and manipulating cell structures. So at the end of that, participants responded pretty favourably, and overall the usability was rated as good or excellent. So I'd like to show you a short video clip from our first pilot, which shows 2 undergraduate students discussing what they thought about the way cells were represented in their usual teaching methods versus in our prototype system. So hopefully it will work. Nope. Okay, never mind. The important bit is at the bottom there. So the girls were talking about how they found what they were looking at and whether it was what they expected. So the important quote there is, you kind of forget that cells are 3D, to be honest. Like when you're not looking at textbooks and PowerPoints, it doesn't enter your head that that's not actually what it looks like. And they were talking about when they're looking at textbooks, it's just lines. That's what the girl was pointing there. She was just drawing lines, depicting that's what she sees the cell as. And didn't think about it as if you're looking at a cell from the outside, you would just see the cell wall there. You wouldn't see all these little squiggles and things coming out. So that was quite encouraging for us at the beginning to see that they're starting to think about new ideas. So for our second pilot study, participants worked as a pair, as a pilot and a co-pilot, to follow a worksheet including tasks requiring to take apart a cell, order the organelles, and to put the cell back together again. And you can see how it was all set up here. That's me wearing the Oculus Rift there to view the 3D space, and we're using the Touch 3D haptic device. So the results of our second pilot gave us some insights into design that we can carry forward. Overall, we were successful in creating an interactive 3D virtual system with a task that actually facilitated discussion amongst the pilot and the co-pilot. So students liked receiving the touch feedback from the haptic interface, but the lack of detailed haptic content at this stage was a drawback. So we found that students had mixed opinions on the interaction and navigation. So some said that the navigation felt very natural to them, whilst others said that it was a bit restrictive. But the Oculus Rift especially had some novelty value there. They really enjoyed using that, and they said it felt they were more immersed in it, in that world. So building on these pilots, we plan to do a main study with younger participants from our partner schools, integrating a haptic system into their biology classrooms as like a circus of activities. So we're planning on a haptic activity involving the cell membrane and active and passive diffusion of particles, which is notoriously hard for students to grasp. And you can see the prototype model here, which shows the membrane. The light blue spheres are representing particles. Oxygen would be the smallest, and something like sodium would be bigger. And the dark blues or channels there as well. But we would be planning to implement the haptics in a way that the students would be able to feel the fluidity of the cell membrane when they press against it. They'll be able to feel the way that oxygen can just pass through the cell membrane, whereas sodium wouldn't be able to get through. And we'd also like to be, we're planning for them to be able to feel the effects of the concentration gradients. So when they're moving particles through the channels, they'll feel the effects of the concentration gradient, whether it's easy to go through or not. So I'd like to introduce a few discussion points. One of the issues that's still in development in this project is how to foster a collaborative learning experience whilst using this environment. So by using the Oculus Rift, I mean, they really enjoyed it, but the students have a visual barrier between them and other students. So encouraging the collaborative learning there is a bit of a challenge. The pilot and co-pilot system did work quite well, although I think we're planning the haptic activity to foster more discussion between the two students. But ways of encouraging collaboration are still being developed for this. This is one of the discussion points put out for this workshop. What are the key challenges of content and representation development? So regarding content and representation of cell biology in haptic environments, some specific content specifics are still actually unknown. So, for example, how the cell membrane changes shape as particles go through it, it's not actually known yet. So how to represent that without creating more misconceptions is a problem. Additionally, how do we represent these structures? It's impossible to be entirely realistic. For example, organelles, they're technically transparent and colourless because they're so small. So that's impractical to represent to students. So that's why textbooks often represent them in sort of bright colours, often the same colour in sort of every textbook. But that leads to the misconceptions that we were talking about before. So a balance between realism and useful representation needs to be made. Also, how do we represent the feel of the cell membrane components? We don't actually know what these things would feel like in real life. So we have to think about how to best portray them haptically. Another discussion point which was raised was how should we assess the impact of these devices on learning educational concepts and skills? So in order to isolate and assess the effects of the haptics in this system, we plan to compare results from two groups of students. So the first group would use the system normally with the haptics enabled, whereas the second group would only be provided with the bare minimum haptic feedback necessary to navigate 3D space. So this means that any haptic feedback designed to be educational wouldn't be available to them. So this way we can assess the educational impact of the haptics in the system. There's also the question of how we assess the students' knowledge of cell biology. In biology, students can often perform well in exams despite misunderstanding fundamental concepts. So the question is which assessment will be most appropriate. So perhaps a mixture of multiple choice and open questions might be sufficient, but we're also looking to do some semi-structured interviews, add some qualitative data in there to be more useful in revealing a richer data of the students' conceptions of the system and how they feel they've learned, and etc. to try and get a bit more information. Okay. And that's it. Thank you very much.
So at this point, I think it'd be good we can shift gears into so kind of for a few minutes before we'll start our rec and touring. I think if there's any kind of questions from the second set of speakers, so I'll open the floor. Please.
Yeah, I got one question for please. So in the beginning of your slide, you mentioned a very fantastic image of the human's brain. And you listed several keywords such as attention control and working memory. So I wonder, have you performed any user study with the Hapkit platform with the attention learning or something?
We haven't. So this result is actually from a paper by Joe Boulder, who's an education researcher, and they did a lot of studies with putting children in MRI machines and seeing which areas of the brain lit up when they did mathematical calculations. We're hoping for Haptic and MRI machines. Yeah, so I would think.
I have a question to Professor Rankin. So in your talk, you mentioned that we don't need scripted lessons, but instead we need better design, careful design sandboxes. But on the other hand, the science education, if you look at the lab classes, they're highly scripted. So why do you think this doesn't work when we introduce a Haptic system?
Yeah, that's a really good question. I haven't completely made up my own mind about it yet. And it's part of where we really struggled here, because we were trying to follow a model of kind of science education to really change one thing, which design with haptics in mind. And we just got so stopped because we were really watching what the students were doing, and we saw this complete just lack of interest as soon as we went into that mode, where it's such a sharp contrast to when they could be more exploratory. That it just seemed counterproductive to continue down that road. And so my advice for Sandbox isn't limited to haptics. It's for other things too. But of course, there's always going to be places where you do need discussion, you do need description, because they need that in order to get to the point where they can really explore. And there's different ways that different educational systems have approached this. At MIT, for the undergrad engineers, their approach was actually in mechanical engineering to throw the students into something with very little structure first, so that they could get motivated by what they needed to know, and then go back and give them the structure later. So they start with unscripted sandbox, big hard goals, and have them really struggle through that, but be very excited about it, and then go and find the structure later. Once they understand, oh, now I know how to do this better, I have a reason to want to learn it. And so that's an alternative approach that's been very successful in some places. So it's not just about haptics, it's much broader.
A question from the assessment. You review different ways of assessing the methods. I mean, when we were thinking about how to do that, what sounds to be the goal is that those kids learn concepts. So we thought, well, we should take the exam that they do, the test that they do before, a pre-test, and then some training, and then post-test.
Yeah.
When you mentioned that.
Yeah, I think that's a really good, very good comment, and yes, that's a very common and good thing to do, and I would say we simply haven't gotten that far. We're still at the design stage of trying to figure out what the learning environments, learning experiences should be. And so we just haven't gotten that far. So instead, we're taking much more baby steps, and we're trying to understand what kind of experiences are going to make kids explore. So going back to the question about why do you need sandboxes, we were trying to get them to explore, just break out and actually try something here. And if you can't get them to do that much, then there's no point in a post-test or pre-test protest. So I guess I was kind of on with that.
Can I just make a follow-up comment to that? So I think you'd think that exams would be the question would be a good assessment mechanism. So one approach was Volca, where we test across different years, but then you've always got the argument that the years might be different. We certainly tried something where we tested the same question pre and post, and then we get the problem that the students have seen the question and they just see this as boring. They've answered the question. Why are we asking to answer the question? So the best we're getting, I think, maybe able to correct my voice, is to just take, this is why the NQT multiple choice questions, because we can randomize questions pre and post.
Yeah.
It's not ideal, but.
And another thing that, so on this, I showed 3 approaches we were taking to actually trying to understand conceptual learning. And the second one was the structured but focus on haptics. And so Richard Davis, the Stanford education student who was leading that effort, actually did do pre and post tests and didn't see a lot of difference. But it was a very small, very, can I say, like, very small sample size. I'm almost afraid to say how small it was. It was very qualitative. So I don't think there's anything that I can really say about the pre-post test. But there was just much, at this stage, there's much more to learn by the qualitative analysis, I would say. And we're still trying to figure out what the should be. And, I know what I was going to say. This thing of transfer and measuring transfer is actually it's a little bit out of my own bailiwick here, but an accepted mechanism of testing conceptual learning and getting away from rote learning. So how well do they learn one concept, or can you kind of ignore that because there's lots of ways they can sort of cheat on that, and then you see how well you can transfer the learning to a different problem. And that's something that you could maybe test in more every way. And you can do that whether it's a structured thing or a simple structured thing.
That's, for example, when you're able to learn how to write or how to teach, of course, usually educational department do. I mean, they take, well, this is exactly what you said, so we are very far from that. But, for example, France, a couple of years ago, made a huge test of using Haptic materials to teach shapes, and it was about 80 classes. And they trained the teachers, and I mean, they made a big investments because somebody in the education ministry believed in that and invested a lot of money in that. But that's what they did. That's what they wanted to know in order to generalize that to the curricula of.
And was it successful?
Actually, it wasn't. If you are Japanese, we had the study that he was really disappointed by the results. And it was an Haptic device. It was Haptics, but not
Well, this would be a good time to switch to our raconteur. Maybe we should get all the speakers.
Yeah, I wonder if we can have the speakers just come up front. I think the idea is to try and get you guys talking to one another a little bit. Some maybe make it more easy. Put some chairs. Sure. You want to take the chairs? Yeah. Yeah. job, is to sort of listen to these wonderful presentations and attempt to identify some kind of cross-cutting themes that we can kind of get you guys talking about amongst yourselves. So sort of give it my best shot, but I'm more than happy to kind of work through this very fluidly. So to begin, I guess as I sat listening, especially this morning, a framework began to develop in my mind, and then Karen came and blew it away, but it's okay. I'm going to go ahead and start with my framework, given I've thought so much little more about it than you have. But in my mind, there were actually sort of three classes of things that I'm hearing about. One is haptics, or the idea of using this type of hardware to teach important concepts in the field of haptics. And then the second, and this is sort of where I've broken out a little bit more, is using it to teach concepts in the sort of supporting fields of haptics, right? For instance, like Karen teaching advanced controls, right? Or Karen teaching interactionism. And then the third was other. So I was close, Karen. I just hadn't simplified it quite as much. But a lot of my thinking is sort of was influenced by that framework I was sort of trying to come up with. And so let me start with teaching about haptics. And the day began with Olivier talking about the engineering week, right? Which was, to my mind, that was sort of in that category. Because you're asking people to build a simulator for doing a needle puncture type of activity. And I felt like that was like, you go through that exercise and you've learned a lot about haptics, it seems to me. So allow me to put it in that category. So a couple of things that you did, it struck me that was a very, very effective example of using haptic technology in teaching. A couple of things that you did there. One was challenge-based learning. Right? At least as I understand it, what you're telling students is your challenge is to build a simulator to do this. Go and figure it out. Right? In fact, the hardware wasn't even given to them. It was the components that were given, right? And so one of my questions for the panel is, what do you think about the importance of this sort of challenge-based paradigm? And is it one that could extend effectively into these second and third, maybe especially the third level? So if I wanted to teach about understanding human cells, does this sort of challenge-based learning with sort of no rules, you haven't put them in the garden where all the pieces are there, but the components perhaps available for which to build things. But that makes sense, or in some of the other areas that we've talked about. So first, that's my first question. Challenge-based learning.
I think it just depends on you. People learn in different ways, and I think for some people, challenge-based learning would be fantastic. I think they would embrace that challenge, and they might have a competitive spirit that would make them really kind of go for it. But I think there are plenty of kids that would kind of leave them out of the loop, that they kind of learn by examples and doing something, seeing something how it's done, and then kind of repeating it, and that's how they learn to do something. So I think it would just kind of depend on the student, honestly.
Does that tie into some of the things that Karen was talking about, the sort of level of STEM preparedness, for instance?
I think so, absolutely. I mean, there might be a correlation between level of STEM preparedness and, the desire to go and build something, for sure.
Actually, I would say that it's a keyword is examples here, and that people who are very experienced designers who professionally do challenge-based design rely very heavily on examples. And it might be examples that seem like code, it might be examples, all of your students did a whole thesis on this topic. But people's repertoire, people's ability to source examples and find them, kind of this so I would say that all levels, starting from very novice, other, but not necessarily high school kids. As long as they can, when they get stuck, they can go out and find examples. It's very helpful
Julia, is it the case when you're observing how students go about solving this challenge you presented them, that examples are key?
Yeah, I mean, what is really important there is that we don't leave them completely alone, right? They need to have quite a bit of supervision from us to answer a lot of questions. Yeah, I mean, in our specific case, they are high school students, so if you would give them the whole problem and leave them without anything, I mean, they shouldn't be able to. So it relies on the teacher being there, I mean, people from us being there. They still have to bring their own ideas. Don't tell them what to do, just guide them through the process. And I think this is was the best way of doing it.
So there's two very big educational researchers at Stanford. One of them is Joe, who I've heard from. The other guy, I forgot his name, but I think he's very well known for like won a Nobel Prize in physics and then said, now I'm gonna do introduction. So they both really present the theory that really anything that brings collaboration, whether it's a challenge or anything else, and brings students to actually talk together, that's what really matters in learning.
That's interesting. So let's hit on this collaboration piece a little bit more. I remember again going back to Olivia, you were talking about teams of 5 or 6 that are working.
Yeah, if I may add as well, so it was a competition among themselves, among the class. And so I didn't quite touch on that point, that they were evaluated at the end by us and several criteria, and the winner one get a diploma from the university, which looked quite fancy.
So there's a whole other element of competition.
Exactly, but it brought motivation for them to kind of make not just the design, but the most original design, or the one that had the best feel, or if not the best feel, the most creative look. Or
yeah, okay. Let's hear from others about this collaboration aspect as well. Have you found that, I mean, I struggle a lot with this with teams, getting all the members engaged and sort of all having a comparable learning experience. So people got stories to tell about collaboration and the use of these technologies.
So for example, one very cool example is there's been studies where professors start the class by saying, look, everybody's gonna get an A. Like I think you're not gonna get an A, I'm gonna come talk to you about it. And then they start this challenge of collaboration. Then students actually, like all of their members get engaged because students are not like, no longer can copy off of me or like I'm gonna do this and they're not gonna do this. And also very interestingly, in the class that Alison taught in Japan, it was kind of like more that model because it was a seminar as opposed to like a creative class. And so there were a lot of students who had no engineering background, and then engineering background helped them assemble things and help them get over their fears, as opposed to competing against them in grades.
That's cool. I wish I knew that I was going to get an A. It sounds actually motivating. Okay, let me move on to into another question. Interesting. We've got just not much. I heard a lot today about hands-on. Now, that's really interesting and kind of a multi-level thing in our business, right? So often when I hear people, not in the field of haptics, talking about hands-on, what they mean, of course, is you want to teach some engineering thing, let's say mechatronics, where you actually got to build it, make it work, and debug it, develop all of those sort of critical thinking skills. I'm wondering, and quite frankly, I'm wondering a lot as we went through the day, whether maybe we've conflated hands-on as in feeling it with hands-on as in, rolling up your shirt and doing something. And so I'm sure some of you have thought about this. And I guess the reason that it concerns me a little bit is that we human beings, we're these kind of soft, mushy things, and so we can kind of feel things in a certain range of mechanical behavior. But you want people to sort of learn to apply these concepts over areas that they can't possibly themselves physically experience. So I was thinking like an example of like when I'm teaching dynamic systems, we tend to deal with mechanical systems that have bandwidths of 100 hertz or something. It's hard to extrapolate from that to how does a quartz crystal work. I mean, it's in every one of your devices, right? It's just a second order system, right? But it's working at 80 gigahertz. So it's hard. It's hard to make those extrapolations. And so I'm just curious what your thoughts are as to really the strengths and the weaknesses or the concerns about putting ourselves into this hands-on world with haptics.
One of the things that I'm looking forward to doing is I remember when I was at Experiential and learned about, so I was a mechanical engineer and I was kind of struggling with electronics. Didn't feel natural to me, but mechanics did. And when I figured out that electronics is kind of the same as mechanics, they're the same relationships, physical relationships between them, there's parallels between them. That was, and then also for fluid dynamics, that was really helpful to me to be able to make those links and apply my intuitive mechanical understanding to these other domains. I think that this, when we've been brainstorming about what would this be good for, you know, what kinds of concepts could you teach kids about using haptics? But well, the mechanical ones are kind of obvious. We teach them about Hooke's law, okay? We talk about strength and capacitance and storage. And now say, okay, in a thermal system or an electronic system, which maybe they have a little hard trouble with capacity, then you can use this to transfer. This is something I want to try and see if it works. If it's actually easier to understand how a capacitor works because you understand how a spring works. And if you can say, oh, it's the same.
See, I think that's an extraordinarily important concept. I think we want to teach people the art of abstraction.
Yes,
right?
yes.
You want to learn something and be able to understand that there's an underlying something or another that applies elsewhere.
So when you said, okay, so I can learn hands-on about 100 hertz because I can feel 100 hertz, and I want to apply that to a quartz crystal. Well, why not? If I can learn it here, can I transfer this and understand, oh, it's the same thing except it's just in this other degree. How do you convey that abstraction so that people can start working with that and still have to be hands-on? I don't really care if they can't feel it anymore as long as they know the basic concept, and now they can abstract it and apply it abstraction and something else. So part of it is jumping. Can you show jumping to the abstraction level?
But the abstraction here, Jordy, is energy, because it's the energy which is the same whether it's an electrical system or a mechanical system.
Well, that's not an abstraction.
I'm
joking. But
yeah, actually, so the abstraction is like the Haptic language. So just like we learn things by looking and we learn things by explaining and by talking and by hearing, is like, can we learn something by feeling it? And maybe the feeling doesn't make sense to the actual physics of the device. If you're teaching about 100 hertz, it doesn't have to be an oscillation. Like maybe it's something else. But then if you apply, if the student learns that something else with learning 100 hertz, then they can apply it to a quartz crystal.
So yeah, first of all, I'd like to really second it. I think the main goal is here not to explore everything, but it's maybe to strengthen some basic concepts. I feel sometimes to just try to give the students along too much and they end up not even understanding the basic concepts. And I think if you can reinforce those, then they might, through abstraction afterwards, be able to extend it to others. And the second thing, I think there is, besides what you mentioned, there is this other hands-on as well. I think your students realize that if they keep putting a lot of torque on their motor, these things get hot. and then they suddenly end up burning one, and then we end up not being so happy, or they have to cable it up. Right? And I think they learn a lot hands-on from that as well.
So that's actually quite interesting because that's a secondary point.
So it's completely on the side basically, or when this caps them. But I still have so much switched off that it really makes them think.
I can't. I really been all day sitting here wanting to ask about capstan versus friction drive. I mean, it seems to be a repeated theme here. And I have a question. For those of you who have gone to the friction drive because it makes things more robust.
Which one?
The friction
Capstan
drive.
is more robust and friction is more shitty, but it's easier to put together.
Well, okay, when I said robust, I guess I meant easy to put together. So yes, we agree on that. And it feels more shitty, you just said. So, and so what about that? Like, those of you who are using it to teach, like control and symptom damage and all, I did not see, I'm being critical here, but I didn't see friction in any of those models. And yet, there's a lot of friction in the systems. And so, how are we reconciling that? How are we reconciling the fact that these things really aren't all that perfect? Certainly. Okay, what do? Do you talk about that part?
Not quite. I mean, we talked about the fact that there is a lot of friction in gear drive, then it's an non-brake drive system, and then we compensate for all the effects of friction.
So you have a mix control, you just loop around.
Yeah, exactly.
That works.
So we play with it.
Okay. So then, okay, I'm going to build on this a little bit then. So, Karen made the point that, if we want to sort of put these out into sort of non-STEM settings or want to teach concepts like basic physics, they want to understand the mass or spring as opposed to, for instance, quality may not be there.
Yeah, well, how much quality do you need?
Right.
And can we even manage what is needed?
So here's where I'm coming from. I read lots of applications of students applying to graduate school, and so often they talk about where they first got excited about engineering. You know where it is? Most of the time, it's Lego. So Lego is an interesting system because whereas I see this sort of emphasis on making things sort of cheap and low cost, open source, Lego is kind of in some sense the opposite of that. I mean, it's a commercial endeavor, right? I mean, these things are made with tremendous precision. They are cheap, right? But they're cheap because of scale, because it achieves scale. And so I wonder what the thoughts here are on the prospects of providing something that's low cost, but in fact high quality, and achieving that through scale. Is there a pathway that you can see toward doing that? I know if we put it in the context of college level education, we probably can't, but are there others?
I just make a point that Mindstorms is not completely cheap.
Okay.
And that might be the comparison. That's the better comparison.
Okay, that's fine, but I guess my point is that quality and inexpensiveness are not necessarily at odds. There's this other factor which is scale. More scale helps drive down price.
I mean, if you open up a company and build these things in mass production, you probably could use them for like $30.
Yeah,
And then they'll be
so I guess my question is would there be any incentive in such a company? Is there like a pathway toward widespread use of this type of technology?
Does it have the sandbox that Karen's making? And yeah.
Okay.
Yeah.
So the limitation is
More on the software.
more on the software and the content creation.
Scratch or not.
Yeah.
I feel that, but I also make another point. I really like the last thing that Lisa showed, which was piggybacking multiple devices together. Is customization of these devices. And so one little challenge, I think that if a company was going to try and sell a bunch of these things, to make it large scale, you would need to follow the Lego model, where you can mix and match and customize, and whether it's personalization, as in making little characters out of them, like the subjects do, or I want to do different things with it. If they were trying to sell one thing that you couldn't modify, I think that would not take off very well. I think that the beauty of this is going to be pieces that you can stick together and do different stuff with, and that would be very exciting. You could really Lego-ize.
Okay. So the customization is
Can I just ask on that general question? I mean, what would you see as a Lego haptic unit? Is it the Haptic Paddle, which is now modular, or is it something more like an educational kit for the console or one of the educational?
Can I also throw out there, if I thought of this sooner, I would have shown it, but there was an awesome paper at PI last month. This is Computer-Human Interaction. It's a huge conference. And someone, from MIT, has built a open source thing where you can build a 2D printer, and not a 3D printer. You can basically build your own 3D printer. You can make a 2-axis printer that you could basically extrude anything you want. And they're going out, and everyone all over the world is doing these hackathon things to build stuff. A lot of the project people do involves food, like constructing elaborately frosted cakes or mountains of celery, ground celery. But anyway, you can build using cardboard, basically laser cut cardboard, and build your own 3-axis printer. Okay. And then you want stuff with a 3D printer. So my point in this is, if you're asking one of those questions, what is the Lego unit? I don't know. They got pretty good mileage out of the unit. This is how you make a basic mechanism. Now go and mess around with it as much as you want. I think that that's too difficult for the market would
the ones I've been talking about here, but I think they have the right idea. Is that there's a really simple basic thing you can do and you can customize it out. And then you can either assemble it in combination or you can just change parts.
So, on that topic, because we had that discussions, because the first we went to classrooms and did workshops with teacher. The first thing the teacher tell us when we say we want to introduce Haptic devices, we don't have any money to buy a paper, so they to them. But we were discussing amongst that, and first we want to know whether it works. So I think if it doesn't work, even when it costs 2,000, then what is the point of trying to make it cheap?
Yeah.
So the first is say, well, we maybe there will be conditions, but we don't know. We still don't know whether we can. I mean, depends. I'm not talking about teaching mechanical engineering skills. I'm teaching, but thinking about teaching other concepts. But we don't know how to do that.
But I think this is the distinction between cost and value, because it has to have a value in the class.
Yes.
It doesn't have value in the class. It got, as you said, cost anything you like. Doesn't matter.
Yeah, it's very nice input. I think we're pretty much out of time. Maybe though, sort of on that note, sort of one final question is: if you were to look in your crystal ball and think about other, is there kind of a killer app out there? I get asked this question all the time, so I feel like I have to pass it on. Everyone's like, what's a killer app for haptics? Well, in the education space, especially with, is there a place where haptics brings unique value? A lot of unique value. Yes.
Yeah, I was going to say, a lot of the discussions that we had while we were deciding what topic we were going to use, we thought about a lot of stuff that is just too abstract for students to conceptualize properly. So we talked about sound, but we also talked about bonds in chemistry as well, things like that. I mean, I know they can make models, like the ball and stick models that they have, but it's not, they can't feel anything from it, it's just what they look at. So to bring something that you can touch to a topic that was previously untouchable, I think
but perhaps wherein the sort of things we do with haptics, force fields, potential fields, etc., are actually very intrinsically important.
Yeah.
It's interesting that many of you probably know that sort of the modern age of haptics was started in Fred First lab. You would see looking at that problem of how you get a feel for the interaction working with. For the first time, someone took a master manipulator and hooked it up to computers. That's a nice elegant example. Very nice.
I looked it up on Google, but I didn't see Minecraft with haptics. It was more like virtual reality Minecraft and haptics. Maybe in education it would be like low cost entry and immersive interesting. Anybody has any idea or any trial on this topic? I'm curious.
You mean like to kind of gamify?
Yeah, gamify, but Lego is the physical world of Minecraft.
Oh.
So everybody knows about it, everybody plays about it, and kids love it. And that would be some opportunity to combine these systems, but all that in research, I'm curious.
It's actually interesting. Minecraft is essentially a shape creation tool, right? You build shapes. It's a virtual environment, you build shapes, and you're interacting with them to kind of even up or not to move or whatever physical modeling, as far as I know.
There is a project.
That's sort of interesting to add physical models.
The Piper, I don't know, you can buy it, and they have adapted Minecraft to do physical computing on it, and you build your circuits and play Minecraft at the same time, and it teaches you how to build your circuits. And they send you the kit, you have to build, there is a Raspberry Pi in it, so you have to build a box with your screen. The SD card has Minecraft on it, and they have electric components. So you build your control board, and you save the planets, basically.
I mean, I think this notion of augmenting reality might be what everybody's touching on. So my kids have Anki, so you used to play video games, racing cars. Now you can build a physical track with physical cars that you drive through an app. And you could imagine incorporating the physics, right, through the app, so you're like, as if you're steering a car, but it's handheld. The interactions with cells or chemical bonds, the interactions with springs. And I think it's this notion of just adding that additional sense to try and give some intuition where maybe we don't have it naturally.
I think that general theme of using haptics to kind of bring the physicality to be it virtual reality, augmented reality, or what we just described, which I'm not sure what category that is.
Or deflecting.
Any thoughts on sort of the power of that type of direction, sort of combining with things that have already gotten sort of the attention of kids and that sort of mass market adoption? Maybe we're getting a little tired.
We're a little over on time, but.
Well, are they from group here? Is there anybody who's got thoughts or final questions? I was asking, building on Marcia's question about the idea of sort of riding the coattails, if you will, of technologies that already have the attention of kids that have mass market adoption. So, to get Minecraft or Haptic or whatever.
I think that's definitely a viable way to go about it. I'll be a bit cautious of like the novelty of like how you use that game, like whether it's Minecraft. Like, I think Minecraft's actually pretty malleable, so it is appropriate for those sort of education cases. But for something like Haptic and stuff, I'm not sure how like malleable it is to like teaching other concepts. So I think it really depends on the origins of that.
A big question here is VR and AR is really getting big now. It's getting cheap. So the marriage of haptics and vision systems and the way people doing virtual reality are begging for haptics to be added to it. I mean, there might be something there that price point of augmented reality versus that there could be possibilities where that is what kids are going to be using in their game systems.
I think that actually opens up a whole new area.
It does.
Where you don't actually need haptics at all. So you could, I think there are certainly things which you can do with these new technologies, VR technologies, where you could put haptics, but the haptics may not add value.
Well,
but
I would
but
say
I think there's still, that's not to say that there's still not a place for haptics as well.
It seems like in virtual reality conferences, all I'm hearing is how desperate they are for haptics. They've reached a point where it's just essential. Like it doesn't work anymore without it.
Or can you share with us what's the problem? Why is VR?
There's people waving their hands around in the air and not touching anything.
There's something about physics.
So I'm not talking about education. I'm not talking about educational applications right now. I'm talking about VR. It's the same problems in there all along, but now the graphics is getting so good. It's sort of.
So when I get in your experience with teaching about the cell, you were using Oculus Rift. Where did the real value come from? Was it the fact that you could explore in a 3D environment, or how much was it due to haptics?
When we did our first pilot, we had the Oculus mounted, so it was sort of mimicking looking at a microscope. But we found that a lot of the students just wanted to take it out and put it on and be immersed in it and to look around and to be able to look at the cell from a different view. So from that, I can only say that they enjoyed the immersiveness of it and being in that world and being able to see this huge, cell in front of them, and then to be able to go into it and look at it. So although there's obviously value there, but a lot of them had already tried the Oculus. It wasn't something brand new.
And you described that there was novelty value, but is that fair, or is there something more intrinsic? I mean, that is, after all, the way we interact with the physical world. Is we're able to understand its chair can move around you to move it. And, that's tough to do without something like calculus supports.
I think it was more they were just excited to use this technology.
Okay.
Yeah, that was the motivation we were talking about. But once they were in there, it wasn't as if they were lost. They knew how to. They weren't lost for interaction.
So were they able to get the level of interaction and learning in the absence of the haptics once they were in?
See, so if you took the haptics away from that, they would, I don't think they'd be able to properly interact with that world well in that 3D space. So if they were just being able to look at it through the Oculus, I don't think it would be as beneficial because that's just going to be a 3D model. Although they can now look around it, there's only so far that can go.
So sort of to Karen's point, you can't.
Interactivity. Walking around and getting into space, that's going very well. But if you actually need to physically interact.
Sure. Or to build on your earlier example, if I was really trying to study how proteins fold or interact, now the actual information isn't necessarily all that visually available. It's something that's probably better delivered through haptics. You still want to be able to look at it and see the 3 dimensions. It's an exciting direction.
I think that's a great place to end.
Yeah.
And I'd just like to thank everyone, Ed especially, for doing a very difficult job today, doing very nicely. To our speakers, who've done a fantastic, very educational day. Thank you. At least for me, and certainly for Chad, pulling this all together. So can we have a round of applause for everyone?
I would just like to inform you that the reception will start earlier than planned. It was supposed to start at 6, but it actually already started.
Yeah, the reception finished 2 minutes ago. Yeah, it worked out well. And output.